Section number 17 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Linda Marie Nielsen, Vancouver, BC. Light Science for Leisure Hours by Richard A. Proctor. The Greatest Sea Wave Ever Known. On August 13, 1868, one of the most terrible calamities which has ever visited a people befell the unfortunate inhabitants of Peru. In that land earthquakes are nearly as common as rainstorms are with us, and shocks by which whole cities are changed into a heap of ruins are by no means infrequent. Yet even in Peru, the land of earthquakes, as Humboldt has termed it, no such catastrophe as that of August 1868 had occurred within the memory of man. It was not one city which was laid in ruins, but a whole empire. Those who perished were counted by tens of thousands, while the property destroyed by the earthquake was valued at millions of pounds sterling. Although so many months have passed since the terrible calamity took place, scientific men have been busily engaged until quite recently in endeavoring to ascertain the real significance of the various events which were observed during and after the occurrence of the earthquake. The geographers of Germany have taken interpreting the evidence afforded by this great manifestation of nature's power. Two papers have been written recently on the great earthquake of August 13, 1868, one by Professor von Hochstetter, the other by Herr von Staudy, which presents an interesting account of the various effects by land and by sea, which resulted from the tremendous upheaving force to which the western flanks of the Peruvian Andes were subjected on that day. The effects on land, although surprising and terrible, yet only differ in degree from those which have been observed in other earthquakes. But the progress of the great sea wave which was generated by the upheaval of the Peruvian shores and propagated over the whole of the Pacific Ocean differs altogether from any earthquake phenomena before observed. Other earthquakes have indeed been followed by oceanic disturbances, but these have been accompanied by terrestrial motions, so as to suggest the idea that they had been caused by the motion of the sea bottom, or of the neighboring land. In no instant has it ever before been known that a well-marked wave of enormous proportions should have been propagated over the largest ocean tract on our globe by an earth shock whose direct action was limited to a relatively small region, and that region not situated in the center but on one side of the wide area traversed by the wave. I propose to give a brief sketch of the history of this enormous sea wave. In the first place, however, it may be well to remind the reader of a few of the more prominent features of this great shock to which this wave owed its origin. It was at Arequipa, at the foot of the lofty volcanic mountain Misti, that the most terrible effects of this great earthquake were experienced. Within historic times Misti had poured forth no lava streams, but that the volcano is not extinct is clearly shown by the fact that in 1542 an enormous mass of dust and ashes was vomited forth from its crater. On August 13, 1868, Misti showed no signs of being disturbed. So far as their volcanic neighbor was concerned, the 44,000 inhabitants of Arequipa had no reason to anticipate the catastrophe which presently befell them. At 5 minutes past 5 an earthquake shock was experienced, which, though severe, seems to have worked little mischief. Half a minute later, however, a terrible noise was heard beneath the earth. A second shock more violent than the first was felt, and then began the swaying motion, gradually increasing in intensity. In the course of the first minute this motion had become so violent that the inhabitants ran in terror out of their houses into the streets and squares. In the next 2 minutes the swaying movement had so increased that the more lightly built houses were cast to the ground, and the flying people could scarcely keep their feet. And now, says von Tschudi, there followed during 2 or 3 minutes a terrible scene. The swaying motion which had hitherto prevailed changed into fierce vertical upheaval. The subterranean roaring increased in the most terrifying manner. Then were heard the heart-piercing shrieks of the wretched people, the bursting of walls, the crashing fall of houses and churches, while over all rolled thick clouds of yellowish-black dust, which, had they been poured forth many minutes longer, would have suffocated thousands. Although the shock had lasted but a few minutes, the whole town was destroyed. Not one building remained uninjured, and there were few which did not lie in shapeless heaps of ruins. At Tacna and Arica the earth shock was less severe, but strange and terrible phenomena followed it. At the former place a circumstance occurred, the cause and nature of which yet remains a mystery. About 3 hours after the earthquake, in other words, at about 8 o'clock in the evening, an intensely brilliant light made its appearance above the neighboring mountains. It lasted for fully half an hour, and it has been ascribed to the eruption of some as yet known volcano. At Arica, the sea wave produced even more destructive effects than had been caused by the earthquake. About 20 minutes after the first earth shock, the sea was seen to retire, as if about to leave the shores wholly dry, but presently its waters returned with tremendous force. A mighty wave, whose length seems immeasurable, was seen advancing like a dark wall upon the unfortunate town, a large part of which was overwhelmed by it. 2 ships, the Peruvian corvette America and the United States double-ender Water Tree, were carried nearly half a mile to the north of Arica, beyond the railroad which runs to Tacna, and there left stranded high and dry. This enormous wave was considered by the English vice consul at Arica to have been fully 50 feet in height. At Chala, 3 such waves swept in after the first shocks of earthquake. They overflowed nearly the whole of the town, the sea passing more than half a mile beyond its usual limits. At Islay and Iquique, similar phenomena were manifested. At the former town the sea flowed in no less than 5 times, and each time with greater force. Afterwards the motion gradually diminished, but even an hour and a half after the commencement of this strange disturbance, the waves still ran 40 feet above the ordinary level. At Iquique the people beheld the inrushing wave, whilst it was still a great way off. A dark blue mass of water, some 50 feet in height, was seen sweeping in upon the town with inconceivable rapidity. An island lying before the harbor was completely submerged by the great wave, which still came rushing on, black with the mud and slime it had swept from the sea bottom. Those who witnessed its progress from the upper balconies of their houses, and presently saw its black mass rushing close beneath their feet, looked on their safety as a miracle. Many buildings were indeed washed away, and in the low-lying parts of the town there was a terrible loss of life. After passing far inland, the waves slowly returned seawards, and strangely enough, the sea, which elsewhere heaved and tossed for hours after the first great wave had swept over it, here came soon to rest. At Callao, a yet more singular instance was afforded of the effect which circumstances may have upon the motion of the sea after a great earthquake has disturbed it. In former earthquakes Callao has suffered terribly from the effects of the great sea wave. In fact, on 2 occasions the whole town has been destroyed, and nearly all its inhabitants have been drowned, though the inrush of precisely such waves as flowed into the ports of Arica and Chala. But upon this occasion the centre of subterranean disturbance must have been so situated that either the wave was diverted from Callao, or more probably 2 waves reached Callao from different sources and at different times, so that the 2 undulations partly counteracted each other. Certain it is that, although the water retreated strangely from the coast near Callao, insomuch that a wide tract of the sea bottom was uncovered, there was no inrushing wave comparable with those described above. The sea afterwards rose and fell in an irregular manner, a circumstance confirming the supposition that the disturbance was caused by the 2 distinct oscillations. 6 hours after the occurrence of the earth shock, the double oscillations seem for a while to have worked themselves into unison, for at this time 3 considerable waves rolled in upon the town. But clearly these waves must not be compared with those which in other instances have made their appearance within half an hour of the earth throes. There is little reason to doubt that if the separate oscillations had reinforced each other earlier, Callao would have been completely destroyed. As it was, a considerable amount of mischief was effected, but the motion of the sea presently became irregular again, and so continued until the morning of August the 14th, when it began to ebb with some regularity. But during the 14th there were occasional renewals of the irregular motion, and several days elapsed before the regular ebb and flow of the sea were resumed. Such were the phenomena presented in the region where the earthquake itself was felt. It will be seen at once that within this region, or rather along that portion of the sea coast which falls within the central region of disturbance, the true character of the sea wave generated by the earthquake could not be recognized. If a rock fall from a lofty cliff into a comparatively shallow sea, the water around the place where the rock has fallen is disturbed in an irregular manner. The sea seems at one place to leap up and down, elsewhere one wave seems to beat against another, and the sharpest eye can detect no law in the motion of the seething waters. But presently outside the scene of disturbance a circular wave is seen to form, and if the motion of this wave be watched, it is seen to present the most striking contrast to the turmoil and confusion at its centre. It sweeps onwards and outwards in a regular undulation. Gradually it loses its circular figure, unless the sea bottom happens to be unusually level, showing that although its motion is everywhere regular, it is not everywhere equally swift. A wave of this sort, though incomparably vaster, swept swiftly away on every side from the scene of the great earthquake near the Peruvian Andes. It has been calculated that the width of this wave varied from 1,000,000 to 5,000,000 feet, or roughly from 200 to 1,000 miles, while, when in mid-Pacific, the length of the wave measured along its summit in a widely curved path from one side to another of the great ocean can not have been less than 8,000 miles. We cannot tell how deep-seated was the centre of subterranean action, but there can be no doubt it was very deep indeed, because otherwise the shock felt in towns separated from each other by hundreds of miles could not have been so nearly contemporaneous. Therefore the portion of the earth's crust upheaved must have been enormous, for the length of the region where the direct effects of the earthquake were perceived is estimated by the Professor von Hochstetter no less than 240 miles. The breadth of the region is unknown, because on one side the slope of the Andes and on the other the ocean concealed the motion of the earth's crust. The great ocean wave swept, as I have said, in all directions around the scene of the earth throe. Over a large part of its course its passage was unnoted, because in the open sea the effects even of so vast an undulation could not be perceived. A ship would slowly rise as the crest of the great wave passed under her, and then as slowly sink again. This may seem strange, at first sight, when it is remembered that in reality the great sea wave we are considering swept at the rate of 300 or 400 sea miles an hour over the larger part of the Pacific. But when the true character of ocean waves is understood, when it is remembered that there is no transference of the water itself at this enormous rate, but simply a transmission of motion, precisely as when in a high wind waves sweep rapidly over a cornfield while yet each cornstalk remains fixed on the ground, it will be seen that the effects of the great sea wave could only be perceived near the shore. Even there, as we will presently see, there was much to convey the impression that the land itself was rising and falling rather than that the deep was moved. But among the hundreds of ships which were sailing upon the Pacific when its length and breadth were traversed by the great sea wave, there was not one in which any unusual motion was perceived. In somewhat less than 3 hours after the occurrence of the earthquake, the ocean wave inundated the port of Coquimbo on the Chilean seaboard, some 800 miles from Arica. An hour or so later it had reached Constitucion, 400 miles farther south, and here for some 3 hours the sea rose and fell with strange violence. Farther south, along the shore of Chile, even to the island of Chiloe, the shore wave travelled, though with continually diminishing force, owing doubtless to the resistance which the irregularities of the shore opposed to its progress. The northerly shore wave seems to have been more considerable, and a moment's study of a chart of the two Americas will show that this circumstance is highly significant. When we remember that the principal effects of the land shock were experienced within that angle which the Peruvian Andes form with the long north and south line of the Chilean and Bolivian Andes, we see at once that, had the centre of the subterranean action been near the scene where the most destructive effects were perceived, no sea wave, or but a small one, could have been sent towards the shores of North America. The protecting shore of northern Peru and Ecuador could not have failed to divert the sea wave towards the west, and though a reflected wave might have reached California, it would only have been after a considerable interval of time, and with dimensions much less than those of the sea wave which travelled southwards. When we see that, on the contrary, a wave of even greater proportions travelled towards the shores of North America, we seem forced to the conclusion that the centre of the subterranean action must have been so far to the west that the sea wave generated by it had a free course to the shores of California. Be this as it may, There can be no doubt that the wave which swept the shores of southern California, rising upwards of 60 feet above the ordinary sea level, was absolutely the most imposing of all the indirect effects of the great earthquake. When we consider that even in San Pedro Bay, fully 5,000 miles from the center of disturbance, a wave twice the height of an ordinary house rolled in with unspeakable violence only a few hours after the occurrence of the earth throe, we are most strikingly impressed with the tremendous energy of the earth's movement. Turning to the open ocean, let us track the great wave on its course past the multitudinous islands which dot the surface of the great Pacific. The inhabitants of the Sandwich Islands, which lie about 6,300 miles from Arica, might have imagined themselves safe from any effects which could be produced by an earthquake taking place so far away from them. But on the night between August 13th and 14th, the sea around this island group rose in a surprising manner, insomuch that many thought the islands were sinking and would shortly subside altogether beneath the waves. Some of the smaller islands, indeed, were for a time completely submerged. Before long, however, the sea fell again, and as it did so the observers found it impossible to resist the impression that the islands were rising bodily out of the water. For no less than 3 days this strange oscillation of the sea continued to be experienced, the most remarkable ebbs and floods being noticed at Honolulu, on the island of Oahu. But the sea wave swept onwards far beyond these islands. At Yokohama, in Japan, more than 10,500 miles from Arica, an enormous wave poured in on August 14th, but at what hour we have no satisfactory record. So far as distance is concerned, this wave affords most surprising evidence of the stupendous nature of the disturbance to which the waters of the Pacific Ocean have been subjected. The whole circumference of the earth is but 25,000 miles, so this wave had traveled over a distance considerably greater than 2/5 of the earth's circumference, a distance which the swiftest of our ships could not traverse in less than 5 or 6 weeks, had been swept over by this enormous undulation in the course of a few hours. More complete details reach us from the southern Pacific. Shortly before midnight the Marquesas Isles and the low-lying Tuamotu group were visited by the great wave, and some of these islands were completely submerged by it. The lonely Opara Isle, where the steamers which run between Panama and New Zealand have their coaling station, was visited at about 11:30 in the evening by a billow which swept away a portion of the coal depot. Afterwards great waves came rolling in at intervals of about 20 minutes, and several days elapsed before the sea resumed its ordinary ebb and flow. It was not until about 2:30 on the morning of August 14th that the Samoa Isles, sometimes called the Navigator Islands, were visited by the great wave. The watchmen startled the inhabitants from their sleep by the cry that the sea was about to overwhelm them, and already, when the terrified people rushed from their houses, the sea was found to have risen far above the highest water mark. But it presently began to sink again, and then commenced a series of oscillations, which lasted for several days, and were of a very remarkable nature. Once in every quarter of an hour the sea rose and fell, but it was noticed that it rose twice as rapidly as it sank. This peculiarity is well worth remarking. The eminent physicist Mallet speaks thus. I follow Lyell's quotation. about the waves which traverse an open sea. The great sea wave, advancing at the rate of several miles a minute, consists, in the deep ocean, of a long, low swell of enormous volume, having an equal slope before and behind, and that so gentle that it might pass under a ship without being noticed; but when it reaches the edge of soundings, its front slope becomes short and steep, while its rear slope is long and gentle. On the shores visited by such a wave, the sea would appear to rise more rapidly than it sank. We have seen that this happened on the shores of the Samoan group, and therefore the way in which the sea rose and fell on the days following the great earthquake gave significant evidence of the nature of the sea bottom in the neighborhood of these islands. As the change of the great wave's figure could not have been quickly communicated, we may conclude with certainty that the Samoan Islands are the summits of lofty mountains, whose sloping sides extend far towards the east. This conclusion affords interesting evidence of the necessity of observing even the seemingly trifling details of important phenomena. The wave which visited the New Zealand Isles was altogether different in character, affording a noteworthy illustration of another remark of Mallet's. He says that where the sea bottom slopes in such a way that there is water of some depth close inshore, the great wave may roll in and do little damage, and that we have seen that so it happened in the case of the Samoan Islands. But he adds that where the shore is shelving there will be first a retreat of the water, and then the wave will break upon the beach and roll far in upon the land. This is precisely what happened when the great wave reached the eastern shores of New Zealand, which are known to shelve down to very shallow water, continuing far away to sea towards the east. At about 3:30 on the morning of August the 14th, the water began to retreat in a singular manner from the port of Lyttelton, on the eastern shores of the southernmost of the New Zealand Islands. At length the whole port was left entirely dry, and so remained for about 20 minutes. Then the water was seen returning like a wall of foam 10 or 12 feet in height, which rushed with a tremendous noise upon the port and town. Towards 5 o'clock the water again retired, very slowly as before, not reaching its lowest ebb until 6. An hour later a second huge wave inundated the port. 4 times the sea retired and returned with great power, at intervals of about 2 hours. Afterwards the oscillation of the water was less considerable, but it had not wholly ceased until August 17th, and only on the 18th did the regular ebb and flow of the tide recommence. Around the Samoan group the water rose and fell once in every 15 minutes, while on the shores of New Zealand each oscillation lasted no less than 2 hours. Doubtless the different depths of water, the irregular conformation of the island groups, and other like circumstances, were principally concerned in producing these singular variations. Yet they do not seem fully sufficient to account for so wide a range of difference. Possibly a cause yet unnoticed may have had something to do with the peculiarity. In waves of such enormous extent, it would be quite impossible to determine whether the course of the wave motion was directed full upon a line of shore or more or less obliquely. It is clear that in the former case the waves would be seen to follow each other more swiftly than in the latter, even though there were no difference in their velocity. Far on beyond the shores of New Zealand the great wave coursed, reaching at length the coast of Australia. At dawn on August 14th, Moreton Bay was visited by 5 well-marked waves. At Newcastle on the Hunter River the sea rose and fell several times in a remarkable manner, the oscillatory motion commencing at 6:30 in the morning. But the most significant evidence of the extent to which the sea wave travelled in this direction was afforded at Port Fairy, Belfast, South Victoria. Here the oscillation of the water was distinctly perceived at midday on August 14th, and yet to reach this point the sea wave must not only have travelled on a circuitous course nearly equal in length to half the circumference of the earth, but must have passed through Bass's Straits, between Australia and Van Diemen's Land, and so have lost a considerable portion of its force and dimensions. When we remember that had not the effects of the earth shock been limited by the shores of South America, a wave of disturbance equal in extent to that which travelled westward would have swept towards the east, we see that the force of the shock was sufficient to have disturbed the waters of an ocean covering the whole surface of the earth. For the sea waves which reached Yokohama in one direction and Port Fairy in another had traversed a distance nearly equal to half the earth's circumference, so that if the surface of the earth were all sea, waves setting out in opposite directions from the centre of disturbance would have met each other at the antipodes of their starting point. It is impossible to contemplate the effects which followed the great earthquake. The passage of a sea wave of enormous volume over fully 1/3 of the earth's surface, and the force with which, at the furthermost limits of its range, the wave rolled in upon shores more than 10,000 miles from its starting place, without feeling that those geologists are right who deny that the subterranean forces of the earth are diminishing in intensity. It may be difficult perhaps to look on the effects which are ascribed to ancient earth throes without imagining for a while that the power of modern earthquakes is altogether less. But when we consider fairly the share which time had in those ancient processes of change, when we see that while mountain ranges were being upheaved or valleys depressed to their present position, race after race and type after type appeared on the earth, and lived out the long lives which belong to races and to types, we are recalled to the remembrance of the great work which the earth's subterranean forces are still engaged upon. Even now continents are being slowly depressed or upheaved. Even now mountain ranges are being raised to a new level. Tablelands are in process of formation, and great valleys are being gradually scooped out. It may need an occasional outburst such as the earthquake of August 1868 to remind us that the great forces are at work beneath the earth's surface. But in reality the signs of change have long been noted. Old shore lines shift their place, old soundings vary, the sea advances in one place and retires in another. On every side nature's plastic hand is at work modeling and remodeling the earth, in order that it may always be a fit abode for those who are to dwell upon it. From Fraser's Magazine, July 1870. End of section 17. Recording by Linda Marie Nielsen, Vancouver, BC.
Section 18 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Light Science for Leisure Hours by Richard A. Proctor. The Usefulness of Earthquakes. We have lately had fearful evidence of the energy of the Earth's internal forces. A vibration which, when considered with reference to the dimensions of the Earth's globe, may be spoken of as an indefinitely minute quivering, limited to an insignificant area, has sufficed to destroy the cities and villages of whole provinces, to cause the death of thousands of human beings, and to effect a destruction of property which must be estimated by millions of pounds sterling. Such a catastrophe as this serves indeed to show how poor and weak a creature man is in presence of the grand workings of nature. The mere throes which accompany her unseen subterranean efforts suffice to crumble man's strongest buildings in a moment into dust, while the unfortunate inhabitants are either crushed to death among the ruins or forced to remain shuddering spectators of the destruction of their homes. At first sight, it may seem paradoxical to assert that earthquakes, fearfully destructive as they have so often proved, are yet essentially preservative and restorative phenomena. Yet this is strictly the case. Had no earthquakes taken place in old times, man would not now be living on the face of the earth. If no earthquakes were to take place in future, the term of man's existence would be limited within a range of time far less than that to which it seems likely, in all probability, to be extended. If the solid substance of the earth formed a perfect sphere in ante-geologic times, that is, in ages preceding those to which our present geologic studies extend, there can be no doubt that there was then no visible land above the surface of the water. The ocean must have formed a uniformly deep covering to the submerged surface of the solid globe. In this state of things, nothing but the earth's subterranean forces could tend to the production of continents and islands. Let me be understood. I am not referring to the possibility or impossibility that lands and seas should suddenly have assumed their present figure without convulsion of any sort. This might have happened, since the Creator of all things can doubtless modify all things according to his will. I merely say that, assuming that in the beginning, as now, he permitted all things to work according to the laws he has appointed, then undoubtedly the submerged earth must have risen above the sea by the action of those very forms of force which produce the earthquake in our own times. However this may be, it is quite certain that when once continents and lands had been formed, there immediately began a struggle between destructive and restorative, rather perhaps than preservative, forces. The great enemy of the land is water, and water works the destruction of the land in two principal ways. In the first place, the sea tends to destroy the land by beating on its shores, and thus continually washing it away. It may seem at first sight that this process must necessarily be a slow one. In fact, many may be disposed to say that it is certainly a slow process, since we see that it does not alter the forms of continents and islands perceptibly in long intervals of time. But, as a matter of fact, we have never had an opportunity of estimating the full effects of this cause, since its action is continually being checked by the restorative forces we shall presently have to consider. Were it not thus checked, there can be little doubt that its effects would be cumulative, for the longer the process continued, that is, the more the land was beaten away, the higher would the sea rise, and the greater power would it have to effect the destruction of the remaining land. I proceed to give a few instances of the sea's power of effecting the rapid destruction of the land when nothing happens to interfere with the local action, premising that this effect is altogether insignificant in comparison with that which would take place even in that particular spot if the sea's action were everywhere left unchecked. The Shetland Isles are composed of substances which seem, of all others, best fitted to resist the disintegrating forces of the sea, namely granite, gneiss, mica slate, serpentine, greenstone, and many other forms of rock. Yet, exposed as these islands are to the uncontrolled violence of the Atlantic Ocean, they are undergoing a process of destruction which, even within historical times, has produced very noteworthy changes. Steep cliffs are hollowed out, says Sir Charles Lyell, into deep caves and lofty arches, and almost every promontory ends in a cluster of rocks imitating the forms of columns, pinnacles, and obelisks. Speaking of one of the islands of this group, Dr. Hibbert says, "The Isle of Stens presents a scene of unequalled desolation. In stormy winters, large blocks of stone are overturned, or are removed from their native beds and hurried to a distance almost incredible. In the winter of 1802, a tabular mass, 8 feet 2 inches by 7 feet and 5 feet 1 inch thick, was dislodged from its bed and carried to a distance of from 80 to 90 feet. In other parts of the Shetland Isles, where the sea has encountered less solid materials, the work of destruction has proceeded yet more effectively. In Roeness, for example, the sea has wrought its way so fiercely that a large cavernous aperture 250 feet long has been hollowed out. But the most sublime scene, says Dr. Hibbert, is where a mural pile of porphyry, escaping the process of disintegration that is devastating the coast, appears to have been left as a sort of rampart against the inroads of the ocean. The Atlantic, when provoked by wintry gales, batters against it with all the force of real artillery, and the waves, in their repeated assaults, have at length forced for themselves an entrance. This breach, named the Grind of the Navire, is widened every winter by the overwhelming surge that, finding a passage through it, separates large stones from its sides and forces them to a distance of no less than 180 feet. In 2 or 3 spots, the fragments which have been detached are brought together in immense heaps, that appear as an accumulation of cubical masses, the product of some quarry. Let us next turn to a portion of the coastline of Great Britain which is neither defended on the one hand by barriers of rock, nor attacked on the other by the full fury of the Atlantic currents. Along the whole coast of Yorkshire we find evidences of a continual process of dilapidation. Between the projecting headland of Flamborough and Spurn Point, the coast of Holderness, the waste is particularly rapid. Many spots which are now mere sandbanks are marked in the old maps of Yorkshire as the sites of ancient towns and villages. Speaking of Hyde, one of these, Pennant says, "Only the tradition is left of this town. Owthorne and its church have been for the most part destroyed, as also Auburn, Hartburn, and Kilnsea." Mr. Phillips, in his Geology of Yorkshire, states that not unreasonable fears are entertained that at some future time Spurn Point itself will become an island or be wholly washed away, and then the ocean, entering into the estuary of the Humber, will cause great devastation. Pennant states that several places, once towns of note upon the Humber, are now only recorded in history, and Ravensburg was at one time a rival of Hull, and a port so very considerable in 1332 that Edward Balliol and the Confederate English barons sailed from hence to invade Scotland, and Henry IV, in 1399, made choice of this port to land at to effect the deposal of Richard II. Yet the whole of this has since been devoured by the merciless ocean. Extensive sands, dry at low water, are to be seen in their stead. The same writer also describes Spurn Point as shaped like a sickle, and the land to the north, he says, was perpetually preyed on by the fury of the German Sea, which devours whole acres at a time. The decay of the shores of Norfolk and Suffolk is also remarkably rapid. Sir Charles Lyell relates some facts which throw an interesting light on the ravages which the sea commits upon the land here. It was computed that when a certain inn was built at Sheringham, 70 years would pass before the sea could reach the spot, the mean loss of land being calculated from previous observations to be somewhat less than 1 yard annually. But no allowance had been made for the fact that the ground sloped from the sea. In consequence of this peculiarity, the waste became greater and greater every year as the cliff grew lower. Between the years 1824 and 1829, no less than 17 yards were swept away, and when Sir Charles Lyell saw the place, only a small garden was left between the building and the sea. I need hardly add that all vestiges of the inn have long since disappeared. Lyell also relates that in 1829 there was a depth of water sufficient to float a frigate at a point where, less than half a century before, there stood a cliff 50 feet high with houses upon it. I have selected these portions of the coast of Great Britain, not because the destruction of our shores is greater here than elsewhere, but as serving to illustrate processes of waste and demolition which are going on around all the shores, not merely of Great Britain, but of every country on the face of the earth. Here and there, as I have said, there are instances in which a contrary process seems to be in action. Low-lying banks and shoals are formed, sometimes along stretches of coast extending for a considerable distance. But when we consider these formations closely, we find that they rather afford evidence of the energy of the destructive forces to which the land is subject than promise to make up for the land which has been swept away. In the first place, every part of these banks consists of the debris of other coasts. Now, we cannot doubt that of earth which is washed away from our shores, by far the larger part finds its way to the bottom of the deep seas. A small proportion only can be brought, by some peculiarity in the distribution of ocean currents, or in the progress of the tidal wave, to aid in the formation of shoals and banks. The larger, therefore, such shoals and banks may be, the larger must be the amount of land which has been washed away never to reappear. And although banks and shoals of this sort grow year by year larger and larger, yet, unless added to artificially, they continue always either beneath the surface of the water in the case of shoals, or but very slightly raised above the surface. Now, if we suppose the destruction of land to proceed unchecked, it is manifest that at some period, however remote, the formation of shoals and banks must come to an end, owing to the continual diminution of the land from the demolition of which they derive their substance. In the meantime, the bed of the sea would be continually filling up. The level of the sea would be continually rising, and thus the banks would be either wholly submerged through the effect of this cause alone, or they would have so slight an elevation above the sea level that they would offer little resistance to the destructive effects of the sea, which would then have no other land to act upon. But we have yet to consider the second principal cause of the wasting away of the land. The cause we have just been dealing with acts upon the shores or outlines of islands and continents. The one we have now to consider acts upon their interior. Many, perhaps, would hardly suppose that the fall of rain upon the land could have any appreciable influence in the demolition of continents, but, as a matter of fact, there are few causes to which geologists attribute more importance. The very fact that enormous deltas have been formed at the mouths of many rivers, in other words, the actual growth of continents through the effects of rainfall, is a proof how largely this cause must tend to destroy and disintegrate the interiors of our continents. Dwelling on this point, Sir Charles Lyell presents the following remarkable illustration. During a tour in Spain, he writes, I was surprised to see a district of gently undulating ground in Catalonia, consisting of red and grey sandstone, and, in some parts, of red marl, almost entirely denuded of herbage, while the roots of the pines, holm oaks, and some other trees were half exposed, as if the soil had been washed away by a flood. Such is the state of the forests, for example, between Oristo and Viche, and near San Lorenzo. But being overtaken by a violent thunderstorm in the month of August, I saw the whole surface, even the highest levels of some flat-topped hills, streaming with mud, while on every declivity the devastation of torrents was terrific. The peculiarities in the physiognomy of the district were at once explained, and I was taught that, in speculating on the greater effects which the direct action of rain may once have produced on the surface of certain parts of England, we need not revert to periods when the heat of the climate was tropical. Combining the effects of the sea's action upon the shores of continents, and of the action of rain upon their interior, and remembering that unless the process of demolition were checked in some way, each cause would act from year to year with new force, one through the effects of the gradual rise of the seabed, and the other through the effects of the gradual increase of the surface of ocean exposed to the vaporizing action of the sun, which increase would necessarily increase the quantity of rain yearly precipitated on the land, we see the justice of the opinion expressed by Sir John Herschel, that, had the primeval world been constructed as it now exists, time enough has elapsed, and force enough directed to that end has been in activity, to have long ago destroyed every vestige of land. We see, then, the necessity that exists for the action of some restorative or preservative force sufficient to counteract the effects of the continuous processes of destruction indicated above. If we consider, we shall see that the destructive forces owe their efficiency to their levelling action, that is, to their influence in reducing the solid part of the earth to the figure of a perfect sphere. Therefore, the form of force which is required to counteract them is one that shall tend to produce irregularities in the surface contour of the earth. And it will be remarked that although upheaval is the process which appears at first sight to be the only effectual remedy to the levelling action of rains and ocean currents, yet the forcible depression of the earth's surface may prove in many instances yet more effective, since it may serve to reduce the sea level in other places. Now, the earth's subterranean forces serve to produce the very effects which are required in order to counteract the continual disintegration of the shores and interior parts of continents. In the first place, their action is not distributed with any approach to uniformity over different parts of the earth's crust, and therefore the figure they tend to give to the surface of that crust is not that of a perfect sphere. This of itself secures the uprising of some parts of the solid earth above the sea level. But this is not all. On a comparison of the various effects due to the action of subterranean forces, it has been found that the forces of upheaval act, on the whole, more powerfully under continents, and especially under the shore lines of continents, while the forces of depression act most powerfully, on the whole, under the bed of the ocean. It need hardly be said that whenever the earth is upheaved in one part, it must be depressed somewhere else. Not necessarily at the same instant, it should be remarked. The process of upheaval may be either momentarily accompanied by a corresponding process of depression, or the latter process may take place by a gradual action of the elastic powers of the earth's crust. But in one way or the other, the balance between upheaval and depression must be restored. Hence, if it can be shown that for the most part the forces of upheaval act underneath the land, it follows, though we may not be able to recognize the fact by obvious visible signs, that processes of depression are taking place underneath the ocean. Now, active volcanoes mark the center of a district of upheaval, and most volcanoes are near the sea, as if, though of course this is not the true explanation, nature had provided against the inroads of the ocean by seating the Earth's upheaving forces just where they are most wanted. Even in earthquake districts which have no active vent, the same law is found to prevail. It is supposed by the most eminent seismologists that earthquake regions around a volcano and earthquake regions apparently disconnected from any outlet differ only in this respect, that in the one case the subterranean forces have had sufficient power to produce the phenomena of eruption, while in the other they have not. In earthquakes, says Humboldt, we have evidence of a volcano-producing force, but such a force, as universally diffused as the internal heat of the globe, and proclaiming itself everywhere, rarely acts with sufficient energy to produce actual eruptive phenomena, and when it does so, it is only in isolated and particular places. Of the influence of the Earth's subterranean forces in altering the level of land, I might quote many remarkable instances, but considerations of space compel me to confine myself to 2 or 3. The slow processes of upheaval or depression may, perhaps, seem less immediately referable to subterranean action than those which are produced during the progress of an actual earthquake. I pass over, therefore, such phenomena as the gradual uprising of Sweden, the slow sinking of Greenland, and, still proceeding westward, the gradual uprising of Nova Scotia and the shores of Hudson's Bay. Remarkable and suggestive as these phenomena really are, and indisputable as the evidence is on which they rest, they will probably seem much less striking to the reader than those which I am now about to quote. On the 19th of November, 1822, a widely felt and destructive earthquake was experienced in Chile. On the next day it was noticed for the first time that a broad line of seacoast had been deserted by the sea for more than 100 miles. A large part of this tract was covered by shellfish, which soon died, and exhaled the most offensive effluvia. Between the old low water mark and the new one, the fishermen found burrowing shells, which they had formerly had to search for amidst the surf. Rocks some way out to sea, which had formerly been covered, were now dry at half ebb tide. Careful measurements showed that the rise of the land was greater at some distance inshore than along the beach. The watercourse of a mill about a mile inland from the sea had gained a fall of 14 inches in little more than 100 yards. At Valparaiso the rise was 3 feet, at Quintero 4 feet. In February 1835 and in November 1837 a large tract of Chile was similarly shaken, a permanent rise of 2 feet following the former earthquake and a rise of 8 feet the latter. The earthquake which took place at Cutch in 1819 is perhaps in some respects yet more remarkable. In this instance, phenomena of subsidence, as well as phenomena of upheaval, were witnessed. The estuary of the Indus, which had long been closed to navigation, being in fact only a foot deep at ebb tide, and never more than 6 feet at flood, was deepened in parts to more than 18 feet at low water. The fort and village of Sindri were submerged, only the tops of houses and walls being visible above the water. But although this earthquake seemed thus to have land-destroying instead of a land-creating effect, yet the instances of upheaval were, even in this case, far more remarkable than those of depression. Immediately after the shock, says Sir Charles Lyell, the inhabitants of Sindri saw at a distance of 5 miles and a half from their village a long elevated mound, where previously there had been a low and perfectly level plain. To this uplifted tract they gave the name of Ulabund, or the Mound of God, to distinguish it from several artificial dams previously thrown across the eastern arm of the Indus. It has been ascertained, he adds, that this new raised country is upwards of 50 miles in length from east to west, running parallel to the line of subsidence which caused the grounds around Sindri to be flooded. The breadth of the elevation is conjectured to be in some parts 16 miles, and its greatest ascertained height above the original level of the delta is 10 feet, an elevation which appears to the eye to be very uniform throughout. From Chambers' Journal, November 7, 1868. End of Section 18. Recording by Linda Johnson. Section 19 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Light Science for Leisure Hours by Richard A. Proctor. The Forcing Power of Rain. There is an old proverb which implies that England need never fear drought, and we have had clear evidence this year, 1868, that an exceptionally dry summer is not necessarily followed by a bad harvest. But I believe that when a balance is carefully struck between the good and the evil effects resulting from excessive drought in England, it will be found that the latter largely prevail. In fact, it is only necessary to observe the effects which have followed the recent wet weather to recognize the fact that rain has a forcing power, the very diminished supply of which at the due season cannot fail to have seriously injurious effects. In various parts of England we see evidences of the action of such a power during the present autumn in the blossoming of trees, in the flowering of primroses and other spring plants, in rich growths of fungi, and in various other ways. It cannot be doubted that there is here a comparative waste of powers which, expended in due season, would have produced valuable results. The modern theories of the correlation of force suffice to show how enormous a loss a country suffers when there is a failure in the supply of rain, or when that supply comes out of its due season. When we consider rain in connection with the causes to which it is due, we begin to recognize the enormous amount of power of which the ordinary rainfall of a country is the representative, and we can well understand how it is that the clouds drop fatness on the earth. The sun's heat is, of course, the main agent, we may almost say the only agent, in supplying the rainfall of a country. The process of evaporation carried on over large portions of the ocean's surface is continually storing up enormous masses of water in the form of invisible aqueous vapor, ready to be transformed into cloud, then wafted for hundreds of miles across seas and continents, to be finally precipitated over this or that country, according to the conditions which determine the downfall of rain. These processes do not appear at first sight indicative of any very great expenditure of force, yet in reality the force equivalent of the rain supply of England alone for a single year is something positively startling. It has been calculated that the amount of heat required to evaporate a quantity of water which would cover an area of 100 square miles to a depth of 1 inch would be equal to the heat which would be produced by the combustion of 500,000 tons of coals. The amount of force of which this consumption of heat would be the equivalent corresponds to that which would be required to raise a weight of upwards of 1,000 millions of tons to a height of 1 mile. Now, when we remember that the area of Great Britain and Ireland is about 120,000 square miles, and that the annual rainfall averages about 25 inches, we see that the force equivalent of the rainfall is enormous. All the coal which could be raised from our English coal mines in hundreds of years would not give out heat enough to produce England's rain supply for a single year. When to this consideration we add the circumstance that the force of rain produces bad as well as good effects, the former when the rain falls at undue seasons or in an irregular manner, the latter only when the rainfall is distributed in the usual manner among the seasons, we see that an important loss accrues to a country in such exceptional years as the present. There are few subjects more interesting than those depending on the correlation of physical forces, and we may add that there are few the study of which bears more largely on questions of agricultural and commercial economy. It is only of late years that the silent forces of nature, forces continually in action, but which are too apt to pass unnoticed and unrecognized, have taken their due place in scientific inquiry. Strangely enough, the subject has been found to have at once a most practical bearing on business relations and an aspect more strikingly poetical than any other subject, perhaps, which men of science have ever taken in hand to investigate. We see the ordinary processes of nature, as they are termed, taking their place in the workshop of modern wealth, and at the same time exhibited in 100 striking and interesting physical relations. What, for instance, can be stranger or more poetical than the contrast which Professor Tyndall has instituted between that old friend of the agriculturist, the wintry snowflake, and the wild scenery of the Alps? "I have seen," he says, "the wild stone avalanches of the Alps, which smoke and thunder down the declivities with a vehemence almost sufficient to stun the observer. I have also seen snowflakes descending so softly as not to hurt the fragile spangles of which they were composed, yet to produce from aqueous vapour a quantity which a child could carry of that tender material demands an exertion of energy competent to gather up the shattered blocks of the largest stone avalanche I have ever seen, and pitch them to twice the height from which they fell." I may point out in this place the important connection which exists between the rainfall of a country and the amount of forest land. I notice that in parts of America attention is being paid with markedly good results to the influence of forests in encouraging rainfall. We have here an instance in which cause and effect are interchangeable. Rain encourages the growth of an abundant vegetation, and abundant vegetation in turn tends to produce a state of the superincumbent atmosphere which encourages the precipitation of rain. The consequence is that it is very necessary to check, before it is too late, the processes which lead to the gradual destruction of forests. If these processes are continued until the climate has become excessively dry, it is almost impossible to remedy the mischief, simply because the want of moisture is destructive to the trees which may be planted to encourage rainfall. Thus, there are few processes more difficult, as has been found by experience in parts of Spain and elsewhere, than the change of an arid region into a vegetation-covered district. In fact, if the region is one of great extent, the attempt to effect such a change is a perfectly hopeless one. On the other hand, the contrary process, that is, the attempt to change a climate which is too moist into one of less humidity, is in general not attended with much difficulty. A judicious system of clearing nearly always leads to the desired result. The dryness of the past year has not been due to the want of moisture in the air, nor to the exceptionally unclouded condition of our skies. I believe that, on the whole, the skies have been rather more cloudy than usual this year. The fact that so little dew has fallen is a sufficient proof that the nights have been, on the whole, more cloudy than usual, since, as is well known, the presence of clouds, by checking the radiation of the earth's heat, prevents or at least diminishes the formation of dew. The fact would seem to be that the westerly and southwesterly winds, which usually blow over England during a considerable part of the year, bringing with them large quantities of aqueous vapour from above the great Gulf Stream, have this year blown somewhat higher than usual. Why this should be is not very easy to say. The height of the vapour-laden winds is usually supposed to depend on the heat of the weather. In summer, for instance, the clouds range higher, and therefore travel farther inland before they fall in rain. In winter, on the contrary, they travel low, and hence the rain falls more freely in the western than in the eastern counties during winter. A similar relation prevails in the Scandinavian peninsula, Norway receiving more rain in winter than in summer, while Sweden receives more rain in summer than in winter. But this summer the rain clouds have blown so much higher than usual as to pass beyond England altogether. Possibly we may find an explanation in the fact that before reaching our shores at all, the clouds were relieved by heavy rainfalls, probably due to some exceptional electrical relations over parts of the Atlantic Ocean. It is stated that the steamships from America this summer were, in many instances, drenched by heavy showers until they neared the coasts of England. From the Daily News, October 5, 1868. End of section 19. Recording by Linda Johnson.
Section number 20 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Light Science for Leisure Hours by Richard A. Proctor. A shower of snow crystals. Yesterday morning, remarkably fine fall of snow stars took place over many parts of London. The crystals were larger and more perfectly formed than is commonly the case in our latitudes, where the conditions requisite for the formation of these beautiful objects are less perfectly fulfilled than in more northerly regions. Many forms were to be noticed which the researches of Scoresby, Glaisher, and Lowe have shown to be somewhat uncommon. Some of my readers will perhaps be surprised to learn that no less than 1,000 different kinds of snow crystals have been noticed by the observers named above, and that a large proportion of them have been figured and described. The patterns are of wonderful beauty. A strange circumstance connected with these objects is the fact that for the most part they are found, on a close examination, to be formed of minute colored crystals, some red, some green, others blue or purple. In fact, all the colors of the rainbow are to be seen in the delicate tracery of these fine hexagonal stars, so that in the perfect whiteness of the driven snow we have an illustration of the well-known fact that the colors of the rainbow combine to form the purest white. For the common snowflake is formed of a large number of such tiny crystals as were falling yesterday, though their beauty is destroyed in the snowflake through the effects of collision and partial melting. It may not be very commonly known that ordinary ice, also, is composed of a combination of crystals presenting all the regularity of formation seen in the snow crystals. This would scarcely be believed by anyone who examined a rough mass of ice taken from the surface of a frozen lake. Yet, if a slice can be cut from the mass and placed in the sun's light, or before a fire, the beautiful phenomena called ice flowers make their appearance. A fairy seems to have breathed upon the ice, and caused transparent flowers of exquisite beauty suddenly to blossom in myriads within it. When we remember that the enormous icebergs of the Arctic and Antarctic seas, the snow-caps which crown the Alps and Andes and Himalayas, and the glaciers which urge their way with resistless force down the mountain valleys, are all made up of these delicate and beautiful snow-flowers, we are struck with the force of the strange contrasts which nature presents to our contemplation. We may say of the snow crystals what Tennyson said of the small sea-shell. Each snow star is frail, but a work divine, made so fairly well, so exquisitely minute, a miracle of design. Yet massed together with all the prodigality of nature's unsparing hand, they crown the everlasting hills, or falling in avalanche and glacier, overwhelm the stoutest works of man, or, in vast islands of floating ice, show themselves to be of force to withstand, year upon year, the shock of cataract seas that snap the 3 Deckers' oaken spine. From the Daily News, March 11th, 1869. End of section number 20. Recording by April 6090, California, United States of America. Section 21 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April 6090, California, United States of America. Light Science for Leisure Hours by Richard A. Proctor. Chapter 21. Long Shots. Our artillerists have paid more attention of late years to the destructive properties of various forms of cannon than to the question of range. It was different when first the rifling of cannon was under discussion. Then the subject was most attentively considered. After accuracy of fire, was the range which might possibly be attained by various improvements in the structure of rifled cannon. Most of my readers will remember how, soon after the construction of Armstrong guns had been commenced in the government factories, a story was spread abroad of the wonderful practice which had been made with this gun at a range of 7 miles. At that tremendous range, a shot had been fired into the middle of a flock of geese, according to one version of the story. But this was presently improved upon, and we were told that a bird had been singled out of the flock by the artillerists, and successfully potted. Many believed this little narrative, though some few, influenced perhaps by the consideration that a flock of geese would not be visible at a distance of 7 miles, were obstinately incredulous. Presently it turned out that the Armstrong gun was incapable of throwing a shot to a distance of 7 miles, so that a certain air of improbability has since attached to the narrative. Still, there were not wanting those who referred to Queen Anne's pocket pistol, the cannon which was able to throw shot across the Straits of Dover. In the fullness of their faith in that mythical piece of ordnance, they refused to believe that the skill of modern artillerists was unequal to the construction of cannon even more effective. If there are any who still believe in the powers ascribed to the fair-famed pocket pistol, they will find their confidence in modern artillery largely shaken by the announcement that it is considered a great matter that one of Whitworth's cannon should have thrown a shot to a distance of very nearly 6 miles and a half. Not only is this so, however, but it is well known that no piece of ordnance has ever flung a projectile to so great a distance since first firearms were invented, and it may be safely predicted that men will never be able to construct a cannon which, as far as range is concerned, will do much better than this one of Mr. Whitworth's. The greatest range which had ever before been attained fell somewhat short of 6 miles. The 7-inch steel gun contrived by Mr. Linnell Thomas had flung a projectile weighing 175 pounds to a distance of 10,075 yards, and according to General Lefroy's Handbook of Artillery, that was the greatest range ever recorded. But Mr. Whitworth's cannon has thrown a shot more than 1,000 yards further. Very few have any idea of the difficulties which oppose themselves to the attainment of a great range in artillery practice. It may seem, at first sight, the simplest possible matter to obtain an increase of range. Let the gun be made but strong enough to bear a sufficient charge, and range seems to be merely a question of the quantity of powder made use of. But in reality the matter is much more complicated. The artillerist has to contrive that the whole of the powder made use of shall be burned before the shot leaves the cannon, and yet the charge shall not explode so rapidly as to burst the cannon. If he use some forms of powder, very useful for special purposes, half the charge would be blown out without doing its share of work. On the other hand, there are some combustibles, as gun cotton and the nitrates, which burn so fast that the gun would be likely to burst before the shot could be expelled. Then again, the shot must fit so closely that there shall be no windage, and yet not so closely as to resist too much the action of the exploding powder. Again, there is the forms of the shot to be considered. A sphere is not the solid which passes most readily through a resisting medium like the air, and yet other projectiles, which are best so long as they maintain a certain position, meet with a greater resistance when once they begin to move unsteadily. The conoid used in ordinary rifle practice, for example, passes much more freely through the air, point first, than an ordinary spherical bullet. But if the point did not travel first, as would happen but for the rifling, or even if the conoidal bullet swayed about on its course, it would meet with more resistance than a spherical bullet. Hence the question of fast or slow rifling has to be considered. Fast rifling gives a greater spin, but causes more resistance to the exit of the shot from the barrel. With slow rifling these conditions are reversed. And then the common notion is that a cannonball travels in the curve called a parabola, and that artillerists have nothing to do but to calculate all about this parabola, and to deduce the range from the initial velocity according to some simple principles depending on the properties of the curve. All this is founded on a complete misapprehension of the true difficulties in the way of the problem. Only projectiles thrown with small velocity from the earth travel in parabolic paths. A cannonball follows a wholly different kind of curve. The resistance of the air, which seems to most persons a wholly insignificant item in the inquiry, is so enormous in the case of a cannonball as to become by far the most important difficulty in the way of the practical artillerist. When a 250-pound shot is hurled with such force from a gun as to cover a range of 6 miles, the resistance of the air is about 40 times the weight of the ball, that is equivalent to a weight of upwards of 4 tons. The range in such a case as this is but a small fraction of that which would be given by the ordinary parabolic theory. As regards artillery practice in war, there are other difficulties in the attainment of a very extended range. Cannon meant for battering down forts cannot possibly be used in the same way that Whitworth's was used at Shoeburyness. The shot flung from this gun at an elevation of 33 degrees could have been watched, it would have been found that it fell to the earth at a much greater angle, that is, much more nearly in a perpendicular direction. On the ordinary parabolic theory, of course, the angle of fall would be the same as the angle of elevation. But under actual circumstances there is an important difference. If forts are to be battered down, however, it will not serve that they should be struck from above. Our artillerists must perforce keep to the old method of pounding away at the face of the forts they attack. Therefore an elevation which is all very well for mortars, that is, when the question merely is of flinging a bomb into a town or fortress, it is utterly unsuited for ordinary artillery. With an elevation of 10 degrees, Whitworth's cannon scarcely projected the 250-pound shot to a distance of 3 miles. The progress of the modern science of gunnery certainly tends to increase the distance at which armies will engage each other. With field artillery, flinging shot to a distance of 2 or 3 miles, and riflemen able to make tolerably sure practice at a distance of 3/4 of a mile, we are not likely often to hear of hand-to-hand conflicts in future warfare. The use of breech-loaders will also tend to the same effect. Hitherto we have scarcely had experience of the results which these changes are to be produced on modern warfare. At Sadowa, breech-loaders did not encounter breech-loaders, and it was easy for the victors in that battle to come to close quarters with their enemies. But in a battle where both sides are armed with breech-loaders, we shall probably see another sort of affair altogether. The bayonet will be an almost useless addition to the soldier's arms. A charge of cavalry upon well-armed infantry will be almost as hopeless as the famous Balaclava charge, and the artillery on either side will have to play a game at long bowls. I venture to anticipate that the first great European war will introduce a total change into the whole system of warlike maneuvers. From the Daily News, November, 1868. End of section number 21.
Section 22 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Light Science for Leisure Hours by Richard A. Proctor. Influence of Marriage on the Death Rate. The Royal Commission on the Law of Marriage has attracted attention to many singular and instructive results of modern statistical inquiry. Not the least important of these is the apparent influence of marriage on the death rate. For several years it has been noticed by statisticians that the death rate of unmarried men is considerably higher than the death rate of married men and widowers. I believe that Dr. Stark, Registrar General for Scotland, was one of the first to call attention to this peculiarity, as evidenced by the results of 2 years' returns for Scotland. But the law has since been confirmed by a far wider range of statistical inquiry. The relative proportion between the death rates of the married and of the unmarried is not absolutely uniform in different countries, but it is fairly enough represented by the following table, which exhibits the mortality per 1,000 of married and unmarried men in Scotland. Ages 20 to 25, husbands and widowers 626, unmarried 1,231. Ages 25 to 80, husbands and widowers 823, unmarried 1,494. Ages 30 to 35, married 865, unmarried 1,594. Ages 35 to 40, married 1,167, unmarried 1,602. Ages 40 to 45, married 1,407, unmarried 1,835. Ages 45 to 50, married 1,704, unmarried 2,118. Ages 50 to 55, married 1,954, unmarried 2,634. Ages 55 to 60, married 2,614, unmarried 2,854. Ages 60 to 65, married 3,563, unmarried 4,454. Ages 65 to 70, married 5,293, unmarried 6,021. Ages 70 to 75, married 8,156, unmarried 10,271. Ages 75 to 80, married 11,785, unmarried 14,394. Ages 80 to 85, married 17,388, unmarried 19,540. From this table we are to understand that out of 100,000 married persons, including widowers, from 20 to 25 years old, 626 die in the course of each year, while out of a similar number of unmarried persons between the same ages, no less than 1,231 die in each year, and in like manner all the other lines of the table are to be interpreted. Commenting on the evidence supplied by the above figures, Dr. Stark stated that bachelorhood is more destructive to life than the most unwholesome trades, or than residence in an unwholesome house or district, where there has never been the most distant attempt at sanitary improvement of any kind. And this view has been very generally accepted not only by the public, but by professed statisticians. Yet, as a matter of fact, I believe that no such inferences can legitimately be drawn from the above table. Dr. Stark appears to me to have fallen into the mistake, which M. Quetelet tells us is so common, of trying to make his statistics carry more weight than they are capable of bearing. It is important that the matter should be put in a just light, for the Royal Commission on the Law of Marriage has revealed no more striking fact than that of the prevalence of immature marriages, and such reasoning as Dr. Stark's certainly cannot tend to discourage these unwise alliances. If death strikes down in 5 years only half as many of those who are married as of those who are unmarried between the ages of 20 and 25, as appears from the above table, and if the proportion of deaths between the two classes goes on continually diminishing in each successive lustre, as is also shown by the above table, it seems reasonable to infer that the death rate would be even more strikingly disproportionate for persons between the ages of 15 and 20 than for persons between the ages of 20 and 25. I believe, indeed, that if Dr. Stark had extended his table to include the former ages, the result would have been such as I have indicated. Yet few will suppose that very youthful marriages can exercise so singularly beneficial an effect. To many, Dr. Stark's conclusion may appear to be a natural and obvious sequitur from the evidence upon which it is founded. Admitting the facts, and I see no reason for doubting them, it may appear at first sight that we are bound to accept the conclusion that matrimony is favorable to longevity. Yet the consideration of a few parallel cases will suffice to show how small a foundation the figures I have quoted supply for such a conclusion. What would be thought, for example, of any of the following inferences? Among hothouse plants there is observed a greater variety and brilliance of color than among those which are kept in the open air. Therefore, the housing of plants conduces to the splendor of their coloring. Or again, the average height of life guardsmen is greater than that of the rest of the male population. Therefore, to be a life guardsman conduces to tallness of stature. Or, to take an example still more closely illustrative of Dr. Stark's reasoning, the average longevity of noblemen exceeds that of untitled persons. Therefore, to have a title is conducive to longevity. Or, borrowing his words, to remain without a title is more destructive to life than the most unwholesome trades, or than residence in an unwholesome house or district where there has never been the most distant attempt at sanitary improvement of any kind. We know that the inference is absurd in each of the above instances, and we are able at once to show where the flaw in the reasoning lies. We know that splendid flowers are more commonly selected for housing, and that life guardsmen are chosen for their tallness, so that we are prevented from falling into the mistake of ascribing splendor of color in the one instance or tallness in the other to the influence of causes which have nothing whatever to do with those attributes. Nor is anyone likely to ascribe the longevity of our nobility to the possession of a title. Yet there is nothing in any one of the above inferences which is in reality more unsound than Dr. Stark's inference from the mortality bills, when the latter are considered with due reference to the principles of interpretation which statisticians are bound to follow. The fact is that, in dealing with statistics, the utmost care is required in order that our inferences may not be pushed beyond the evidence afforded by our facts. In the present instance, we have simply to deal with the fact that the death rate of unmarried men is higher than the death rate of married men and widowers. From this fact, we cannot reason, as Dr. Stark has done, to a simple conclusion. All that we can do is to show that one of 3 conclusions must be adopted. Either matrimony is favorable, directly or indirectly, to longevity in a degree sufficient wholly to account for the observed peculiarity, or a principle of selection, the effect of which is such as, on the whole, to fill the ranks of married men from among the healthier and stronger portion of the community, operates in a sufficient degree to account wholly for the observed death rates, or, lastly, the observed death rates are due to the combination, in some unknown proportion, of the 2 causes just mentioned. No reasonable doubt can exist, as it seems to me, that the third is the true conclusion to be drawn from the evidence supplied by the mortality bills. Unfortunately, the conclusion thus deduced is almost valueless, because we are left wholly in doubt as to the proportion which subsists between the effects to be ascribed to the two causes thus shown to be in operation. It scarcely required the evidence of statistics to prove that each cause must operate to some extent. It is perfectly obvious, on the one hand, that although hundreds of men who would be held by insurance companies to be bad lives may contract marriage, yet, on the whole, a principle of selection is in operation, which must tend to bring the healthier portion of the male community into the ranks of the married, and to leave the unhealthier in the state of bachelorhood. A little consideration will show also that, on the whole, the members of the less healthy trades, very poor persons, habitual drunkards, and others whose prospects of long life are unfavorable, must, on the average of a large number, be more likely to remain unmarried than those more favorably situated. Another fact drawn from the Registrar General's return suffices to prove the influence of poverty on the marriage rate. I refer to the fact that marriages are invariably more numerous in seasons of prosperity than at other times. Improvident marriages are undoubtedly numerous, but prosperity and adversity have their influence, and that influence not unimportant on the marriage returns. On the other hand, it is perfectly obvious that the life of a married man is likely to be more favorable to longevity than that of a bachelor. The mere fact that a man has a wife and family depending upon him will suffice to render him more careful of his health, less ready to undertake dangerous employments, and so on, and there are other reasons which will occur to everyone for considering the life of a married man better, in the sense of the insurance companies, than that of a bachelor. In fact, while we are compelled to reject Dr. Stark's statement that bachelorhood is more destructive to life than the most unwholesome trades, or than residence in an unwholesome house or district where there has never been the most distant attempt at sanitary improvement of any kind, we may safely accept his opinion that statistics prove the truth of one of the first natural laws revealed to man. It is not good that man should live alone. From the Daily News, October 17, 1868. End of section 22. Recording by Linda Johnson. Section 23 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Light Science for Leisure Hours by Richard A. Proctor. The Topographical Survey of India. At the close of the war with Tipu Sahib, Major Lambton planned the triangulation of the country lying between Madras and the Malabar coast, a district which had been roughly surveyed during the progress of the war by Colonel Mackenzie. The Duke of Wellington gave his approval to the project, and his brother, the Governor-General of India, and Lord Clive, son of the great Clive, Governor of Madras, used their influence to aid Major Lambton in carrying out his design. The only astronomical instrument made use of by the first survey party was one of Ramsden's zenith sectors, which Lord Macartney had placed in the hands of Dinwiddie, the astronomer, for sale. A steel chain, which had been sent with Lord Macartney's embassy to the Emperor of China, and refused, was the only apparatus available for measuring. Thus began the great trigonometrical survey of India, a work whose importance it is hardly possible to overestimate. Conducted successively by Colonel Lambton, Sir George Everest, Sir Andrew Waugh, and Lieutenant Colonel Walker, the present superintendent, the trigonometrical survey has been prosecuted with a skill and accuracy which renders it fairly comparable with the best work of European surveyors. But to complete in this style the survey of the whole of India would be the work of several centuries. The trigonometrical survey of Great Britain and Ireland has been already more than a century in progress and is still unfinished. It can therefore be imagined that the survey of India, nearly 10 times the size of the British Isles, and presenting difficulties 100-fold greater than those which the surveyor in England has to encounter, is not a work which can be quickly completed. But the growing demands of the public service have rendered it imperatively necessary that India should be rapidly and completely surveyed. This necessity led to the commencement of the Topographical Survey of India, a work which has been pushed forward at a surprising rate during the past few years. My readers may form some idea of the energy with which the survey is in progress from the fact that Colonel Thuillier's report for the season 1866–67 announces the charting of an area half as large as Scotland, and the preparatory triangulation of an additional area nearly half as large as England. In a period of 30 years, with but few surveying parties at first, and a slow increase in their number, an area of 160,000 square miles has been completed and mapped by the Topographical Department. The revenue surveyors have also supplied good maps on a similar scale of 364,000 square miles of country during the 20 years ending in 1866. Combining these results, we have an area of 524,000 square miles, or upwards of 4 times that of Great Britain and Ireland. For all this enormous area, the surveyors have the records in a methodical and systematic form, fit for incorporation in the Atlas of India. Nor does this estimate include the older revenue surveys of the northwestern provinces, which, for want of proper supervision in former years, were never regularly reduced. The records of these surveys were destroyed in the Mutiny, chiefly in Hazambaw and the Southwestern Frontier Agency. The whole of these districts remain to be gone over in a style very superior to that of the last survey. The extent of the country which has been charted may lead to the impression that the survey is little more than a hasty reconnaissance. This, however, is very far indeed from being the case. The preliminary triangulation, which is the basis of the topographical survey, is conducted with extreme care. In the present report, for instance, we find that the discrepancies between the common sides of the triangles, in other words, the discrepancies between the results obtained by different observers, are in some cases less than 1/10 of an inch per mile. In others, they are from 1 inch to a foot per mile. And in the survey of the Kosya and Garo hills, where observations had to be taken to large objects such as trees, rocks, etc., with no defined points for guidance, the results differ by as much as 26 inches per mile. These discrepancies must not only be regarded as insignificant in themselves, but must appear yet more trifling when it is remembered that they are not cumulative, inasmuch as the preliminary triangulation is itself dependent on the great trigonometrical survey. Let us understand clearly what are the various forms of survey which are or have been in progress in India. There are 3 forms to be considered. 1. The great trigonometrical surveys. 2. The revenue surveys. And 3. The topographical surveys. Great trigonometrical operations are extended in a straight course from one measured base to another. Every precaution which modern skill and science can suggest is taken in the measurement of each baseline and in the various processes by which the survey is extended from one baseline to the other. The accuracy with which work of this sort is conducted may be estimated from the following instance. During the progress of the Ordnance Survey of Great Britain and Ireland, a baseline nearly 8 miles long was measured near Lough Foyle in Ireland, and another nearly 7 miles long on Salisbury Plain. Trigonometrical operations were then extended from Lough Foyle to Salisbury Plain, a distance of about 340 miles, and the Salisbury baseline was calculated from the observations made over this long arc. The difference between the measured and calculated values of the baseline was less than 5 inches. As we have stated, the trigonometrical survey of India will bear comparison with the best work of our surveyors in England. A revenue survey is prosecuted for the definition of the boundaries of estates and properties. The operations of such a survey are, therefore, carried on conformably to those boundaries. The topographical survey of a country is defined by Sir A. Scott Waugh to imply the measurement and delineation of the natural features of a country and the works of man thereon, with the object of producing a complete and sufficiently accurate map. Being free from the trammels of boundaries of properties, the principal lines of operations must conform to the features of the country and objects to be surveyed. The only safe basis for the topographical survey of a country is a system of accurate triangulation, and where the extent of country to be surveyed is large, there will always be a great risk of the accumulation of error in the triangulation itself, which must, therefore, be made to depend on the accurate results obtained by the great trigonometrical operations. In order to secure this result, fixed stations are established in the vicinity of the great trigonometrical series. Where this plan cannot be adopted, a network of large symmetrical triangles is thrown over the district to be surveyed, or boundary series of triangles are carried along the outline of the district or along convenient internal lines. The former of these methods is applicable to a hilly district, the latter to a flat country. When the district to be surveyed has been triangulated, the work of filling in the topographical details is commenced. Each triangle being of moderate extent, with sides from 3 to 5 miles in length, and the angular points being determined, as we have seen, with great exactness, it is evident that no considerable error can occur in filling in the details. Hence, methods can be adopted in the final topographical work which would not be suitable for triangulation. The triangles can either be measured up, or the observer may traverse from trigonometrical point to point, taking offsets and intersections, or, lastly, he may make use of the plane table. The two first methods require little comment, but the principle of plane tabling enters so largely into Indian surveying that this notice would be incomplete without a brief account of this simple and beautiful method. The plane table is a flat board turning on a vertical pivot. It bears the chart on which the observer is planning the country. Suppose now that 2 points A and B are determined, and that we require to mark in the position of a third point C. It is clear that if we observed with a theodolite the angles ABC and BAC, we might lay these down on the chart with a protractor, and so the position of C would be determined, with an accuracy proportioned to the care with which the observations were made and the corresponding constructions applied to the chart. But in plane tabling, a more direct plan is adopted. A ruler bearing sights, resembling those of a rifle, is so applied that the edge passing through the point A on the chart, the observer being situated at the real station A, passes through the point B on the chart, the line of sight passing through the real station B. The table being fixed in the position thus obtained, the ruler is next directed so that its edge passes through A, while the line of sight points to C. A line is now ruled with a pencil through A towards C. In a similar manner, the table having been removed to the station B, a pencil line is drawn through the point B on the chart towards C. The two lines thus drawn determine by their intersection the place of C on the chart. The above is only one instance of the modes in which a plane table can be applied. There are several others. Usually the magnetic compass is employed to fix the position of the table in accordance with the true bearing of the cardinal points. Also, the bearings of several points are taken around each station, and thus a variety of tests of the correctness of the work become applicable. Into such details as these I need not here enter. It is sufficient that my readers should have been enabled to recognize the simple principles on which plane tabling depends, and the accuracy with which, when suitable precautions are taken, it can be applied as a method of observation subsidiary to the ordinary trigonometrical processes. A hilly country, says Sir A. Waugh, offers the fairest field for the practice of plane table surveys, and the more rugged the surface, the greater will be the relative advantages and facilities this system possesses over the methods of actual measurement. On the other hand, in flat lands, the plane table works at a disadvantage, while the traverse system is facilitated. Consequently, in such tracts, the relative economy of the two systems does not offer so great a contrast as in the former. In closely wooded or jungly tracts, all kinds of survey operations are prosecuted at a disadvantage, but in such localities the commanding points must be previously cleared for trigonometrical operations, which facilitates the use of the table. In whatever way the topographical details have been filled in, a rigorous system of check must be applied to the work. The system adopted is that of running lines across ground that has been surveyed. This is done by the head of the party or by the chief assistant surveyor. A sufficient number of points are obtained in this way for comparison with the work of the detail surveyors, and when the discrepancies exceed certain limits, the work in which they appear is rejected. Owing to the extremely unhealthy, jungly, and rugged nature of the ground in which nearly all the Indian surveys have been progressing, it has not always been found practicable to check by regularly chained lines. There are, however, other modes of testing plane table surveys, and as these entail less labor and expense in hilly and jungly tracts, and are quite as effective if thoroughly carried out, they have been adopted generally, while the measured routes or check lines have only been pursued under more favorable conditions. Colonel Thuillier states that the inspection of the work of every detailed surveyor in the field has been rigorously enforced, and the work of the field season is not considered satisfactory or complete unless this duty has been attended to. The rules laid down to ensure accuracy in the survey are, first, that the greatest possible number of fixed points should be determined by regular triangulation. Secondly, that the greatest possible number of plane table fixings should be made use of within each triangle. And lastly, that eye sketching should be reduced to a minimum. If these rules are well attended to, the surveyor can always rely on the value of the work performed by his subordinates. But all these conditions cannot be secured in many parts of the ground allotted to the several topographical parties, owing to the quantity of forest land and the extremely rugged nature of the country. Hence arises the necessity for test lines to verify the details, or for some vigorous system of check, and this is more especially the case where native assistants are employed. So soon as the country has been accurately planned, the configuration of the ground has to be sketched up. This process is the end and aim of all the preceding work. The first point attended to is the arterial system, or water drainage, constituting the outfall of the country, whence are deduced the lines of greatest depression of the ground. Next, the watersheds or ridges of hills are traced in, giving the highest level. Lastly, the minor or subordinate features are drawn in with the utmost precision attainable. The outlines of tableland should be well defined, says Sir A. Waugh, and ranges of hills portrayed with fidelity carefully representing the watersheds or divortia aquarum, the spurs, peaks, depressions or saddles, isthmuses, or connecting links of separate ranges and other ramifications. The depressed points and isthmuses are particularly valuable as being either the sites of ordinary passes or points which new roads should conform to. And here we must draw a distinction between survey and reconnaissance. It is absolutely necessary in making a survey that the outlines of ground as defined by ridges, watercourses, and feet of hills should be rigorously fixed by actual observation and careful measurement. In reconnoitering, more is trusted to the eye. The scale of the Indian topographical survey is that of 1 inch per mile, the scale of half an inch per mile being only resorted to in very densely wooded or jungly country, containing a few inhabitants and little cultivated, or where the climate is so dangerous that it is desirable to accelerate the progress of the survey. On the scale of 1 inch per mile, the practiced draftsman can survey about 5 square miles of average country per day. In intricate ground, intersected by ravines or covered by hills of irregular formation, the work proceeds much more slowly. On the other hand, in open and nearly level country, or where the hills have simple outlines, the work will cost less and proceed more rapidly. On the scale of 1 inch per mile, all natural features, such as ravines or watercourses, more than 1/4 of a mile in length, can be clearly represented. Villages, towns, and cities can be shown, with their principal streets and roads, and the outlines of fortifications. The general figure and extent of cultivated, waste, and forest lands can be delineated with more or less precision according to their extent. Irrigated rice lands should be distinctly indicated, since they generally exhibit the contour of the ground. The relative heights of hills and depths of valleys should be determined during the course of a topographical survey. These vertical elements of a survey can be ascertained by trigonometrical or by barometrical observations, or by a combination of both methods. The barometer, says Sir A. Waugh, is more especially useful for determining the level of low spots from which the principal trigonometrical stations are invisible. In using this instrument, however, in combination with the other operations, the relative differences of heights are to be considered the quantities sought, so that all the results may be referable to the original trigonometrical station. The height above the sea level of all points coming under any of the following heads is especially to be determined, for the purpose of illustrating the physical relief of the country. First, the peaks and highest points of ranges. Second, all obligatory points required for engineering works, such as roads, drainage, and irrigation, viz., the highest points or necks of valleys, the lowest depressions or passes in ranges, the junctions of rivers, and débouchements of rivers from ranges, the height of inundation level, at moderate intervals of about 3 miles apart. Third, principal towns or places of note. Of the various methods employed to indicate the steepness of slope, that of eye contouring seems alone to merit special comment. In true contouring, regular horizontal lines at fixed vertical intervals are traced over a country and plotted onto the maps. This is an expensive and tedious process, whereas eye contouring is easy, light, and effective. On this system, all that is necessary is that the surveyor should consider what routes persons moving horizontally would pursue. He draws lines on his chart approximating as closely as possible to these imaginary lines. It is evident that when lines are thus drawn for different vertical elevations, the resulting shading will be dark or light according as the slope is steep or gentle. This method of shading affords scope as well for surveying skill as for draftsmanship. From Once a Week, May 1, 1869. End of Section 23. Recording by Linda Johnson.
Section number 24 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April 6090, California, United States of America. Light Science for Leisure Hours by Richard A. Proctor. Chapter 24. A Ship Attacked by Swordfish. I have always been puzzled to imagine how the 29 knights of fame, described in the Lay of the Last Minstrel, managed to drink the red wine through the helmet bard. But in nature we meet with animals who seem almost as inconveniently armed as those chosen knights, who quitted not by their armor bright, neither by day nor yet by night. Amongst such animals the swordfish may be recognized as one of the most uncomfortably armed creatures in existence. The shark has to turn on his back before he can eat, and the attitude scarcely seems suggestive of a comfortable meal, but the swordfish can hardly even by that arrangement get his awkwardly projecting snout out of the way. Yet doubtless this feature, which seems so inconvenient, is of great value to Xiphias. In some way as yet unknown it enables him to get his living. Whether he first kills some of his neighbors with his instrument and then eats him at his leisure, or whether he plunges it deep into the larger sort of fish, and attaching himself to them in this way, sucks nutriment from them while they are yet alive, is not known to naturalists. Certainly he is fond of attacking whales, but this may result not so much from gastronomic tastes as from a natural antipathy, envy, perhaps, at their superior bulk. Unfortunately for himself, Xiphias, though cold-blooded, seems a somewhat warm-tempered animal, and when he is angered, he makes a bull-like rush upon his foe, without always examining with due care whether he is likely to take anything by his motion. And when he happens to select for attack a stalwart ship, and to plunge his horny beak through 13 or 14 inches of planking, with perhaps a stout copper sheathing outside it, he is apt to find some difficulty in retreating. The affair usually ends by his leaving his sword embedded in the side of the ship. In fact, no instance has ever been recorded of a swordfish recovering his weapon, if I may use the expression, after making a lunge of this sort. Last Wednesday the Court of Common Pleas, rather a strange place, by the by, for inquiring into the natural history of fishes, was engaged for several hours in trying to determine under what circumstances a swordfish might be able to escape scot-free after thrusting his snout into the side of a ship. The gallant Dreadnought, thoroughly repaired and classed A1 at Lloyd's, had been insured for 3,000 lire against all the risks of the seas. She sailed on March 10, 1864, from Colombo for London. 3 days later the crew, while fishing, hooked a swordfish. Xiphias, however, broke the line, and a few moments after leaped half out of the water, with the object, it would seem, of taking a look at his persecutor, the Dreadnought. Probably he satisfied himself that the enemy was some abnormally large catechin, which it was his natural duty to attack forthwith. But this as it may, the attack was made, and at 4 o'clock next morning the captain was awakened with the unwelcome intelligence that the ship had sprung a leak. She was taken back to Colombo, and thence to Cochin, where she was hove down. Near the keel was found a round hole, an inch in diameter, running completely through the copper sheathing and planking. As attacks by swordfish are included among sea risks, the insurance company was willing to pay the damages claimed by the owners of the ship, if only it could be proved that the hole had really been made by a swordfish. No instance had ever been recorded in which a swordfish had been able to withdraw his sword after attacking a ship. A defense was founded on the possibility that the hole had been made in some other way. Professor Owen and Mr. Frank Buckland gave their evidence, but neither of them could state quite positively whether a swordfish, which had passed its beak through 3 inches of stout planking, could withdraw without the loss of its sword. Mr. Buckland said that the fish had no power of backing, and expressed his belief that he could hold a swordfish by the beak. But then he admitted that the fish had considerable lateral power, and might so wriggle its sword out of a hole. And so the insurance company will have to pay nearly £600, because an ill-tempered fish objected to being hooked, and took its revenge by running full tilt against the copper sheathing and oak planking. From the Daily News, December 11th, 1868. End of section number 24.
Section 25 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Light Science for Leisure Hours by Richard A. Proctor. The Safety Lamp. From the Daily News, December 4, 1868. As recent colliery explosions have attracted a considerable amount of attention to the principle of the safety lamp, and questions have arisen respecting the extent of the immunity which the action of this lamp secures to the miner, it may be well for me briefly to point out the true qualities of the lamp. In the Davy lamp, a common oil light is surrounded by a cylinder of wire gauze. When the air around the lamp is pure, the flame burns as usual, and the only effect of the gauze is somewhat to diminish the amount of light given out by the lamp. But as soon as the air becomes loaded with the carbureted hydrogen gas generated in the coal strata, a change takes place. The flame grows larger and less luminous. The reason of the change is this: the flame is no longer fed by the oxygen of the air, but is surrounded by an atmosphere which is partly inflammable, and the inflammable part of the gas, so fast as it passes within the wire cylinder, is ignited and burns within the gauze. Thus the light now given out by the lamp is no longer that of the comparatively brilliant oil flame, but is the light resulting from the combustion of carbureted hydrogen, or fire damp, as it is called, and every student of chemistry is aware that the flame of this gas has very little illuminating power. So soon as the miner sees the flame thus enlarged and altered in appearance, he should retire. But it is not true that explosion would necessarily follow if he did not do so. The danger is great because the flame within the lamp is in direct contact with the gauze, and if there is any defect in the wirework, the heat may make for itself an opening which, though small, would yet suffice to enable the flame within the lamp to ignite the gas outside. So long, however, as the wire gauze continues perfect, even though it become red hot, there will be no explosion. No authority is required to establish this point, which has been proved again and again by experiment, but I quote Professor Tyndall's words on the subject to remove some doubts which have been entertained on the matter. Although a continuous explosive atmosphere, he says, may extend from the air outside through the meshes of the gauze to the flame within, ignition is not propagated across the gauze. The lamp may be filled with an almost lightless flame. Still, explosion does not occur. A defect in the gauze, the destruction of the wire at any point by oxidation hastened by the flame playing against it, would cause an explosion, and so on. It need hardly be said, however, that, imprudent as miners have often been, no miner would remain where his lamp burned with the enlarged flame, indicative of the presence of fire damp. The lamp should also be at once extinguished. But here we touch on a danger which undoubtedly exists, and, so far as has yet been seen, cannot be guarded against by any amount of caution. Supposing the miner sought to extinguish the lamp by blowing it out, an explosion would almost certainly ensue, since the flame can be forced mechanically through the meshes, though it will not pass through them when it is burning in the ordinary way. Now, of course, no miner who had been properly instructed in the use of the safety lamp would commit such a mistake as this. But it happens, unfortunately, that sometimes the fire damp itself forces the flame of the lamp through the meshes. The gas frequently issues with great force from cavities in the coal, in which it has been pent up, when the pick of the miner breaks an opening for it. In these circumstances, an explosion is inevitable if the issuing stream of gas happen to be directed full upon the lamp. Fortunately, however, this is a contingency which does not often arise. It is one of those risks of coal mining which seem absolutely unavoidable by any amount of care or caution. It would be well if it were only such risks as these that the miners had to face. Another peculiarity sometimes noticed when there is a discharge of fire damp is worth mentioning. It happens occasionally that the light will be put out, owing to the absolute exclusion of air from the lamp. This, however, can only happen when the gas issues in so large a volume that the atmosphere of the pit becomes irrespirable. With the exception of the one risk which we have pointed out above, the Davy lamp may be said to be absolutely safe. It is necessary, however, that caution and intelligence should be exhibited in its use. On this point, Professor Tyndall remarks that unfortunately the requisite intelligence is not often possessed, nor the requisite caution exercised by the miner, and the consequence is that even with the safety lamp, explosions still occur. And he suggests that it would be well to exhibit to the miner, in a series of experiments, the properties of the valuable instrument which has been devised for his security. Mere advice will not enforce caution, he says, but let the miner have the physical image of what he is to expect clearly and vividly before his mind, and he will find it a restraining and monitory influence long after the effect of cautioning words has passed away. A few words on the history of the invention may be acceptable. Early in the present century, a series of terrible catastrophes in coal mines had excited the sympathy of enlightened and humane persons throughout the country. In the year 1813, a society was formed at Sunderland to prevent accidents in coal mines, or at least to diminish their frequency, and prizes were offered for the discovery of new methods of lighting and ventilating mines. Dr. William Reed Clanny, of Bishop Wearmouth, presented to this society a lamp which burnt without explosion in an atmosphere heavily loaded with fire damp, for which invention the Society of Arts awarded him a gold medal. The Reverend Dr. Gray called the attention of Sir Humphrey Davy to the subject, and that eminent chemist visited the coal mines in 1815, with the object of determining what form of lamp would best be suited to meet the requirements of the coal miners. He invented two forms of lamp before discovering the principle on which the present safety lamps are constructed. This principle, the property, namely, that flame will not pass through small apertures, had been, we believe, discovered by Stephenson, the celebrated engineer, some time before, and a somewhat angry controversy took place respecting Davy's claim to the honor of having invented the safety lamp. It seems admitted, however, by universal consent, that Davy's discovery of the property above referred to was made independently, and also that he was the first to suggest the idea of using wire gauze in place of perforated tin. In comparing the present frequency of colliery explosions with what took place before the invention of the safety lamp, we must take into consideration the enormous increase in the coal trade since the introduction of steam machinery. The number of miners now engaged in our coal mines is far in excess of the number employed at the beginning of the present century. Thus, accidents in the present day are at once more common, on account of the increased rapidity with which the mines are worked, and when they occur, there are more sufferers, so that the frequency of colliery explosions in the opening years of the present century and the number of deaths resulting from them are in reality much more significant than they seem to be at first sight. But even independently of this consideration, the record of the colliery accidents which took place at that time is sufficiently startling. 72 persons were killed in the colliery at North Biddick at the commencement of the present century. 2 explosions in 1805 at Hepburn and Oxclose left no less than 43 widows and 151 children unprovided for. In 1808, 90 persons were killed in a coal pit at Lumley. On May 24, 1812, 91 persons were killed by an explosion at Felling Colliery near Gateshead, and many more such accidents might readily be enumerated. From the Daily News, December 4, 1868. End of section 25.
Section 26 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, visit LibriVox.org. Recording by Clive Catterall. Light Science for Leisure Hours by Richard A. Proctor. The Dust We Have to Breathe. A microscopist, Mr. Dancer, F.R.A.S., has been examining the dust of our cities. The results are not pleasing. We had always recognized city dust as a nuisance, and had supposed that it derived the peculiar grittiness and flintiness of its structure from the constant macadamizing of city roads. But it now appears that the effects produced by dust, when, as is usual, it finds its way to our eyes, our nostrils, and our throats, are as nothing compared with the mischief it is calculated to produce in a more subtle manner. In every specimen examined by Mr. Dancer, animal life was abundant, but the amount of molecular activity, such is the euphemism under which what is exceedingly disagreeable to contemplate is spoken about, is variable according to the height at which the dust is collected. And of all heights which these molecular wretches could select for the display of their activity, the height of 5 feet is that which has been found to be the favourite. Just at the average height of the foot passenger's mouth, these moving organisms are always waiting to be devoured and to make us ill. And this is not all. As if animal abominations were insufficient, a large proportion of vegetable matter also disports itself in the light dust of our streets. The observations show that in thoroughfares where there are many animals engaged in the traffic, the greater part of the vegetable matter thus floating about consists of what has passed through the stomachs of animals, or has suffered decomposition in some way or other. This unpleasing matter, like the molecular activity, floats about at a height of 5 feet or thereabouts. After this, one begins to recognize the manner in which some diseases propagate themselves. What had been mysterious in the history of plagues and pestilences seems to receive at least a partial solution. Take cholera, for example. It has been shown by the clearest and most positive evidence that this disease is not propagated in any way save one, that is, by the actual swallowing of the cholera poison. In Professor Thudicham's masterly paper on the subject in the Monthly Microscopical Journal, it is stated that doctors have inhaled a full breathing from a person in the last stage of this terrible malady without any evil effects. Yet the minutest atom of the cholera poison received into the stomach will cause an attack of cholera. A small quantity of this matter drying on the floor of the patient's room, and afterwards caused to float about in the form of dust, would suffice to prostrate a houseful of people. We can understand, then, how matter might be flung into the streets, and after drying, its dust be wafted through a whole district, causing the death of hundreds. One of the lessons to be learned from these interesting researches of Mr. Dancer is clearly this, that the watering cart should be regarded as one of the most important of our hygienic institutions. Supplemented by careful scavenging, it might be effective in dispossessing many a terrible malady which now holds sway from time to time over our towns. From the Daily News, March the 6th, 1869. End of section 26. Section 27 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, visit LibriVox.org. Recording by Clive Catterall. Light Science for Leisure Hours by Richard A. Proctor. Photographic Ghosts. On the outskirts of the ever-widening circle lighted up by science, there is always a borderland wherein superstition holds sway. The arts and sciences may drive away the vulgar hobgoblin of darker days, but they bring with them new sources of illusion. The ghosts of old could only gibber. The spirits of our day can read and write and play on diverse musical instruments and quote Shakespeare and Milton. It is not, therefore, altogether surprising to learn that they can take photographs also. You go to have your photograph taken, we will suppose, desiring only to see your own features depicted on the cut, and lo! the spirits have been at work, and a photographic phantom makes its appearance beside you. It is true, this phantom is of a hazy and dubious aspect. The dull mechanic ghost is indistinct, and may be taken for anyone. Still, it is not difficult for the eye of fancy to trace in it the lineaments of some departed friend, who, it is to be assumed, has come to be photographed along with you. In fact, photography, according to the spiritualist, resembles what Byron called the lighting of the mind, which out of things familiar, undesigned, when least we deem of such, calls up to view the spectres whom no exorcism can bind. The phenomena of spiritual photography were first observed some years since, and a set of carte photographs were sent from America to Dr. Walker of Edinburgh, in which photographic phantoms were very obviously, however indistinctly, discernible. More recently, an English photographer noticed a yet stranger circumstance, though he was too sensible to seek for a supernatural interpretation of it. When he took a photograph with a particular lens, there could be seen not only the usual portrait of the sitter, but at some little distance a faint double, exactly resembling the principal image. Superstitious minds might find this result even more distressing than the phantom photographic friend. To be visited by the departed through the medium of a lens is at least not more unpleasing than to hold converse with spirits through an ordinary rapping medium. But the appearance of a double, or fetch, has ever been held by the learned in ghostly lore to signify approaching death. Fortunately, both one and the other appearance can be very easily accounted for without calling in the aid of the supernatural. At a recent meeting of the Photographical Society, it was shown that an image may often be so deeply impressed upon the glass that the subsequent cleaning of the plate, even with strong acids, will not completely remove the picture. When the plate is used for receiving another picture, the original image makes its reappearance, and as it is too faint to be recognizable, a highly susceptible imagination may readily transform it into the image of a departed friend. The double is generated by the well-known property of double refraction, obtained by a lens under certain circumstances of unequal pressure, or sometimes by inequalities in the process of annealing. So vanish two ghosts which might have been more or less troublesome to those who are ready to see the supernatural in commonplace phenomena. Will the time ever come when no more such phantoms will remain to be exorcised? From the Daily News, March the 2nd, 1869. End of section 27.
Section 28 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a recording by Joanne Crosby. Light Science for Leisure Hours by Richard A. Proctor. The Oxford and Cambridge Rowing Styles. Whatever opinion we may have of the result of the approaching contest, 1869, there can be no doubt that this year, as in former years, there is a striking dissimilarity between the rowing styles of the dark blue and the light blue oarsmen. This dissimilarity makes itself obvious whether we compare the two boats as seen from the side, or when the line of sight is directly along the length of either. Perhaps it is the latter aspect that an unpracticed eye will most readily detect the difference I am speaking of. Watch the Cambridge boat approaching you from some distance, or receding, and you will notice, in the rise and fall of the oars, as so seen, the following peculiarities. A long stay of the oar in the water, a quick rise from and return to the water, the oars remaining out of the water for the briefest possible interval of time. In the case of the Oxford boat, quite a different appearance is presented. There is a short stay in the water, a sharp rise from it and return to it, and between these the oars appear to hang over the water for a perceptible interval. It is, however, when the boats are seen from the side that the meaning of these peculiarities is detected, and also that the fundamental distinction between the two styles is made apparent to the experienced eye. In a Cambridge boat, we recognize the long stroke and lightning feather. Inculcated in the old trustees on rowing, in the Oxford boat we see these conditions reversed, and in their place the waiting feather and lightning stroke. By the waiting feather I do not refer to what is commonly understood by slow feathering, but to a momentary pause, scarcely to be detected when the crew is rowing hard, before the simultaneous dash of the oars upon the first grip of the stroke, and observing more closely, which by the way is no easy matter, as either boat dashes swiftly past, we detect the distinct peculiarities of work by which the two styles are severely arrived at. In the Cambridge crew, we see the first part of the stroke done with the shoulders, precisely according to the old-fashioned models, the arms straight and the body has fallen back to an almost upright position. Then comes the sharp drop back of the shoulders beyond the perpendicular of the arms, simultaneously doing their work, so that as the swing back is finished, the back of the hands just touch the ribs in feathering. All these things are quite in accordance with what used to be considered the perfection of rowing, and indeed this style of rowing has some important good qualities and a very handsome appearance. The lightning feather also, which follows the long sweeping stroke, is theoretically perfect. Now in the case of the Oxford crew, we observe a style which at first sight seems less excellent. As soon as the oars are dashed down and catch their first hold of the water, the arms as well as the shoulders of each oarsman are at work. The result is that when the back has reached an upright position, the arms have already reached the chest and the stroke is finished. Thus the Oxford stroke takes a perceptibly shorter time than the Cambridge stroke. It is also necessarily somewhat shorter in the water. One would therefore say it must be less effective. Especially would an unpracticed observer form this opinion, because the Oxford stroke seems to be much shorter in range than it is in reality. There we have the secret of its efficiency. It is actually as long as the Cambridge stroke, but is taken in a perceptibly shorter time. What does this mean but that the oar is taken more sharply, and therefore much more effectively through the water? Much more effectively so far as the actual conditions of the contest are concerned. The modern racing outrigger requires a sharp impulse, because it will take almost any speed we can apply to it. It will also retain that speed between the strokes, a consideration of great importance. The old-fashioned racing eights required to be continually under propulsion. The lightning feather was a necessity in this case, for between every stroke the boat would lag terribly with a slow feathering crew. I do not say, of course, that the speed of a light outrigged craft does not diminish between the strokes. Anyone who has watched a closely contested bumping race and noticed the way in which its sharply cut bow of the pursuing boat draws up to the rudder of the other as by a succession of impulses, although either boat seen alone would seem to sweep on with almost uniform speed, will know that the motion of the lightest boat is not strictly uniform. But there is an immense difference between the almost imperceptible loss of way of a modern 8 and the dead lag in the old-fashioned craft. And hence we get the following important consideration. Whereas with the old boats it was useless for a crew to attempt to give a very quick motion to their boat by a sharp, sudden lift, this plan is calculated to be, of all others, the most effective with the modern racing 8. It may be seen, at first sight, that after all the result of the Cambridge style should be as effective as that of the other, if arms and shoulders do their work in both crews with equal energy, which we may assume to be the case, and if the number of strokes per minute is equal, the actual propulsion energy ought to be equal likewise. A little consideration will show that this is a fallacy. If two men pull at a weight together, they will move it further with a given expenditure of energy than if the first one and then the other apply his strength to the work, and what is more to the purpose, they will be able to move it faster. So shoulders and arms working simultaneously will give a greater propulsion power than when working separately, even though in the latter case each works with its fullest energy. And not only so, but the simultaneous use of arms and shoulders, that sharpness of motion can alone be given which is essential to the propulsion of a modern racing boat. I have said that the two crews are severely rowing in the style which has lately been peculiar to their respective universities. But the Cambridge crew is rowing in that form of the Cambridge style which brings it nearest to the requirement of modern racing. The faults of the style are subdued, so to speak, and its best qualities brought out effectively. In one or two of the long series of defeats lately sustained by Cambridge, the reverse has been the case. At present, too, there is a certain roughness about the Oxford crew, which encourages the hopes of the light blue supporters. But it must be admitted that this roughness is rather apparent than real, great as it seems, and it will doubtless disappear before the day of encounter. I venture to predict that the time of the approaching race, taken in conjunction with the state of the tide, will show that the present crews to be at least equal to the average. End of section 28.
Section 29 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Light Science for Leisure Hours by Richard A. Proctor. Betting on Horse Races, or the State of the Odds. There appears every day in the newspapers an account of the betting on the principal forthcoming races. The betting on such races as the 2,000 guineas, the Derby, and the Oaks often begins more than a year before the races are run, and during the interval the odds laid against the different horses engaged in them vary repeatedly, in accordance with the reported progress of the animals in their training, or with what is learned respecting the intentions of their owners. Many who do not bet themselves find an interest in watching the varying fortunes of the horses which are held by the initiated to be leading favorites, or to fall into the second rank, or merely to have an outside chance of success. It is amusing to notice, too, how frequently the final state of the odds is falsified by the event, how some rank outsider will run into the first place, while the leading favorites are not even placed. It is in reality a simple matter to understand the betting on races or contests of any kind, yet it is astonishing how seldom those who do not actually bet upon races have any inkling of the meaning of those mysterious columns which indicate the opinion of the betting world respecting the probable results of approaching contests, equine or otherwise. Let us take a few simple cases of odds to begin with, and, having mastered the elements of our subject, proceed to see how cases of greater complexity are to be dealt with. Suppose the newspapers inform us that the betting is 2 to 1 against a certain horse for such and such a race, what inference are we to deduce? To learn this, let us conceive a case in which the true odds against a certain event are as 2 to 1. Suppose there are 3 balls in a bag, one being white, the others black. Then, if we draw a ball at random, it is clear that we are twice as likely to draw a black as to draw a white ball. This is technically expressed by saying that the odds are 2 to 1 against drawing a white ball, or 2 to 1 on, that is, in favor of, drawing a black ball. This being understood, it follows that when the odds are said to be 2 to 1 against a certain horse, we are to infer that in the opinion of those who have studied the performance of the horse and compared it with that of the other horses engaged in the race, his chance of winning is equivalent to the chance of drawing one particular ball out of a bag of 3 balls. Observe how this result is obtained. The odds are 2 to 1, and the chance of the horse is as that of drawing one ball out of a bag of 3, 3 being the sum of the two numbers 2 and 1. This is the method followed in all such cases. Thus, if the odds against a horse are 7 to 1, we infer that the cognoscenti consider his chance equal to that of drawing one particular ball out of a bag of 8. A similar treatment applies when the odds are not given as so many to 1. Thus, if the odds against a horse are as 5 to 2, we infer that the horse's chance is equal to that of drawing a white ball out of a bag containing 5 black and 2 white balls, or 7 in all. We must notice also that the number of balls may be increased to any extent, provided the proportion between the total number and the number of a specified color remains unchanged. Thus, if the odds are 5 to 1 against a horse, his chance is assumed to be equivalent to that of drawing one white ball out of a bag containing 6 balls, only one of which is white, or to that of drawing a white ball out of a bag containing 60 balls, of which 10 are white, and so on. This is a very important principle, as we shall now see. Suppose there are 2 horses, amongst others, engaged in a race, and that the odds are 2 to 1 against one, and 4 to 1 against the other. What are the odds that one of the 2 horses will win the race? This case will doubtless remind my readers of an amusing sketch by Leech, called, if I remember rightly, Signs of the Commission. 3 or 4 undergraduates are at a wine, discussing matters equine. One propounds to his neighbor the following question: "I say, Charlie, if the odds are 2 to 1 against Rataplan and 4 to 1 against Quick March, what's the betting about the pair?" "Don't know, I'm sure," replies Charlie, "but I'll give you 6 to 1 against them." The absurdity of the reply is, of course, very obvious. We see at once that the odds cannot be heavier against a pair of horses than against either singly. Still, there are many who would not find it easy to give a correct reply to the question. What has been said above, however, will enable us at once to determine the just odds in this or any similar case. Thus, the odds against one horse being 2 to 1, his chance of winning is equal to that of drawing one white ball out of a bag of 3, one only of which is white. In like manner, the chance of the second horse is equal to that of drawing one white ball out of a bag of 5, one only of which is white. Now, we have to find a number which is a multiple of both the numbers 3 and 5. 15 is such a number. The chance of the first horse, modified according to the principle explained above, is equal to that of drawing a white ball out of a bag of 15, of which 5 are white. In like manner, the chance of the second is equal to that of drawing a white ball out of a bag of 15, of which 3 are white. Therefore, the chance that one of the two will win is equal to that of drawing a white ball out of a bag of 15 balls, of which 8, 5 added to 3, are white. There remain 7 black balls, and therefore the odds are 8 to 7 on the pair. To impress the method of treating such cases on the mind of the reader, let us take the betting about 3 horses, say 3 to 1, 7 to 2, and 9 to 1 against the 3 horses respectively. Then their respective chances are equal to the chance of drawing 1 white ball out of 4, 1 only of which is white; 2 a white ball out of 9, of which 2 only are white; and 3 1 white ball out of 10, 1 only of which is white. The least number which contains 4, 9, and 10 is 180, and the above chances, modified according to the principle explained above, become equal to the chance of drawing a white ball out of a bag containing 180 balls when 45, 40, and 18 respectively are white. Therefore, the chance that one of the 3 will win is equal to that of drawing a white ball out of a bag containing 180 balls, of which 103, the sum of 45, 40, and 18, are white. Therefore, the odds are 103 to 77 on the 3. One does not hear in practice of such odds as 103 to 77, but betting men, whether or not they apply just principles of computation to such questions is unknown to me, manage to run very near the truth. For instance, in such a case as the above, the odds on the 3 would probably be given as 4 to 3, that is, instead of 103 to 77, or 412 to 308, the published odds would be equivalent to 412 to 309. And here a certain nicety in betting has to be mentioned. In running the eye down the list of odds, one will often meet such expressions as 10 to 1 against a horse offered, or 10 to 1 wanted. Now, the odds of 10 to 1 taken may be understood to imply that the horse's chance is equivalent to that of drawing a certain ball out of a bag of 11. But if the odds are offered and not taken, we cannot infer this. The offering of the odds implies that the horse's chance is not better than that above mentioned, but the fact that they are not taken implies that the horse's chance is not so good. If no higher odds are offered against the horse, we may infer that his chance is very little worse than that mentioned above. Similarly, if the odds of 10 to 1 are asked for, we infer that the horse's chance is not worse than that of drawing 1 ball out of 11. If the odds are not obtained, we infer that his chance is better, and if no lower odds are asked for, we infer that his chance is very little better. Thus, there might be 3 horses, A, B, and C, against whom the nominal odds were 10 to 1, and yet these horses might not be equally good favorites, because the odds might not be taken, or might be asked for in vain. We might accordingly find 3 such horses arranged thus: odds A, 10 to 1 wanted; B, 10 to 1 taken; C, 10 to 1 offered. Or these different stages might mark the upward or downward progress of the same horse in the betting. In fact, there are yet more delicate gradations marked by such expressions respecting certain odds as offered freely, offered, offered and taken, meaning that some offers only have been accepted; taken, taken and wanted, wanted, and so on. As an illustration of some of the principles I have been considering, let us take from the day's paper the state of the odds respecting the 2,000 guineas. It is presented in the following form: 2,000 guineas, 7-2 against Rosicrucian, offered. 6-1 against Pace, offered. 7-1 wanted. 10-1 against Greensleeve, offered. 100-7 against Blue Gown, offered. 180-80 against Sir J. Hawley's lot, taken. This table is interpreted thus: bettors are willing to lay the same odds against Rosicrucian as would be the true mathematical odds against drawing a white ball out of a bag containing 2 white and 7 black balls, but no one is willing to back the horse at this rate. On the other hand, higher odds are not offered against him. Hence it is presumable that his chance is somewhat less than that above indicated. Again, bettors are willing to lay the same odds against Pace as might fairly be laid against drawing 1 white ball out of a bag of 7, 1 only of which is white, but backers of the horse consider that they ought to get the same odds as might be fairly laid against drawing the white ball when an additional black ball had been put into the bag. As respects Greensleeve and Blue Gown, bettors are willing to lay the odds which there would be, respectively, against drawing a white ball out of a bag containing 1. 11 balls, 1 only of which is white, and 2. 107 balls, 7 only of which are white. Now, the 3 horses, Rosicrucian, Greensleeve, and Blue Gown, all belong to Sir Joseph Hawley, so that the odds about the 3 are referred to in the last statement of the list just given. And since none of the offers against the 3 horses have been taken, we may expect the odds actually taken about Sir Joseph Hawley's lot to be more favorable than those obtained by summing up the 3 former in the manner we have already examined. It will be found that the resulting odds offered against Sir J. Hawley's lot, estimated in this way, should be, as nearly as possible, 132-80. We find, however, that the odds taken are 180-80. Hence, we learn that the offers against some or all of the 3 horses are considerably short of what backers require, or else that some person has been induced to offer far heavier odds against Sir J. Hawley's lot than are justified by the fair odds against his horses severally. I have heard it asked why a horse is said to be a favorite, though the odds may be against him. This is very easily explained. Let us take as an illustration the case of a race in which 4 horses are engaged to run. If all these horses had an equal chance of winning, it is very clear that the case would correspond to that of a bag containing 4 balls of different colors, since in this case we should have an equal chance of drawing a ball of any assigned color. Now, the odds against drawing a particular ball would clearly be 3-1. This, then, should be the betting against each of the 3 horses. If any one of the horses has less odds offered against him, he is a favorite. There may be more than one of the 4 horses thus distinguished, and in that case the horse against which the least odds are offered is the first favorite. Let us suppose there are 2 favorites, and that the odds against the leading favorite are 3-2, those against the other 2-1, and those against the best non-favorite 4-1, and let us compare the chances of the 4 horses. I have not named any odds against the 4th because, if the odds against all the horses but one are given, the just odds against that one are determinable, as we shall see immediately. The chance of the leading favorite corresponds to the chance of drawing a ball out of a bag in which are 3 black and 2 white balls, 5 in all. That of the next to the chance of drawing a ball out of a bag in which are 2 black and 1 white ball, 3 in all. That of the third to the chance of drawing a ball out of a bag in which are 4 black balls and 1 white one, 5 in all. We take then the least number containing both 5 and 3, that is 15, and then the number of white balls corresponding to the chances of the 3 horses are respectively 6, 5, and 3, or 14 in all, leaving only 1 to represent the chance of the 4th horse, against which the odds are therefore 14 to 1. Hence the chances of the 4 horses are respectively as the numbers 6, 5, 3, and 1. I have spoken above of the published odds. The statements made in the daily papers commonly refer to wagers actually made, and therefore the uninitiated might suppose that everyone who tried would be able to obtain the same odds. This is not the case. The wagers which are laid between practised betting men afford very little indication of the prices which would be forced, so to speak, upon an inexperienced bettor. Bookmakers, that is, men who make a series of bets upon several or all of the horses engaged in a race, naturally seek to give less favorable terms than the known chances of the different horses engaged would suffice to warrant. As they cannot offer such terms to the initiated, they offer them, and in general success, fully to the inexperienced. It is often said that a man may so lay his wagers about a race as to make sure of gaining money whichever horse wins the race. This is not strictly the case. It is, of course, possible to make sure of winning if the bettor can only get persons to lay or take the odds he requires to the amount he requires, but this is precisely the problem which would remain insoluble if all bettors were equally experienced. Suppose, for instance, that there are 3 horses engaged in a race with equal chances of success. It is readily shown that the odds are 2 to 1 against each, but if a bettor can get a person to take even betting against the first horse, A, a second person to do the like about the second horse, B, and a third to do the like about the third horse, C, and if all these bets are made to the same amount, say 1,000, then inasmuch as only one horse can win, the bettor loses 1,000 on that horse, say A, and gains the same sum on each of the 2 horses B and C. Thus, on the whole, he gains 1,000, the sum laid out against each horse. If the layer of the odds had laid the true odds to the same amount on each horse, he would neither have gained nor lost. Suppose, for instance, that he laid 1,000 to 500 against each horse, and A won. Then he would have to pay 1,000 to the backer of A, and to receive 500 from each of the backers of B and C. In like manner, a person who had backed each horse to the same extent would neither lose nor gain by the event, nor would a backer or layer who had wagered different sums necessarily gain or lose by the race. He would gain or lose according to the event. This will at once be seen on trial. Let us next take the case of horses with unequal prospects of success. For instance, take the case of the 4 horses considered above, against which the odds were respectively 3 to 2, 2 to 1, 4 to 1, and 14 to 1. Here, suppose the same sum laid against each, and for convenience let this sum be 84, because 84 contains the numbers 3, 2, 4, and 14. The layer of the odds wagers 84 to 56 against the leading favorite, 84 to 42 against the second horse, 84 to 21 against the third, and 84 to 6 against the fourth. Whichever horse wins, the layer has to pay 84. But if the favorite wins, he receives only 42 on one horse, 21 on another, and 6 on the third. That is 69 in all, so that he loses 15. If the second horse wins, he has to receive 56, 21, and 6, or 83 in all, so that he loses 1. If the third horse wins, he receives 56, 42, and 6, or 104 in all, and thus gains 20. And lastly, if the fourth horse wins, he has to receive 56, 42, and 21, or 119 in all, so that he gains 35. He clearly risks much less than he has a chance, however small, of gaining. It is also clear that in all such cases the worst event for the layer of the odds is that the favorite should win. Accordingly, as professional bookmakers are nearly always layers of odds, one often finds the success of a favorite spoken of in the papers as a great blow for the bookmakers, while the success of a rank outsider will be described as a misfortune to backers. But there is another circumstance which tends to make the success of a favorite a blow to layers of the odds, and vice versa. In the case we have supposed, the money actually pending about the four horses, that is, the sum of the amount laid for and against them, was 140 as respects the favorite, 126 as respects the second, 105 as respects the third, and 90 as respects the fourth. But, as a matter of fact, the amounts pending about the favorites bear always a much greater proportion than the above to the amounts pending about outsiders. It is easy to see the effect of this. Suppose, for instance, that instead of the sums 84 to 56, 84 to 42, 84 to 21, and 84 to 6, a bookmaker has laid 8400 to 5600, 840 to 420, 84 to 21, and 14 to 1, respectively, then it will easily be seen that he would lose 7,958 by the success of the favorite, whereas he would gain 4,782 by the success of the second horse, 5,937 by that of the third, and 6,027 by that of the fourth. I have taken this as an extreme case. As a general rule, there is not so great a disparity as has been here assumed between the sums pending on favorites and outsiders. Finally, it may be asked whether, in the case of horses having unequal chances, it is possible that wagers can be so proportioned, just odds being given and taken, that, as in the former case, a person backing or laying against all the four shall neither gain nor lose. It is so. All that is necessary is that the sum actually pending about each horse shall be the same. Thus, in the preceding case, if the wagers 9 to 6, 10 to 5, 12 to 3, and 14 to 1 are either laid or taken by the same person, he will neither gain nor lose by the event, whatever it may be. And, therefore, if unfair odds are laid or taken about all the horses, in such a manner that the amounts pending on the several horses are equal or nearly so, the unfair bettor must win by the result. Say, for instance, that instead of the above odds, he lays 8 to 6, 9 to 5, 11 to 3, and 13 to 1 against the four horses respectively. It will be found that he must win 1. Or if he takes the odds 18 to 11, 20 to 9, 24 to 5, and 28 to 1, the just odds being 18 to 12, 20 to 10, 24 to 6, and 28 to 2, respectively, he will win 1 by the race, so that by giving or taking such odds to a sufficiently great amount, a bettor would be certain of pocketing a large sum, whatever the event of a given race might be. In every instance, a man who bets on a race must risk his money, unless he can succeed in taking unfair advantages over those with whom he bets. My readers will conceive how small must be the chance that an unpracticed bettor will gain anything but dearly bought experience by speculating on horse races. I would recommend those who are tempted to hold another opinion to follow the plan suggested by Thackeray in a similar case, to take a good look at professional and practiced betting men, and to decide which of those men they are most likely to get the better of in turf transactions. From Chambers' Journal, July 1869. End of section 29. Recording by Linda Johnson.
Section 30 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. Light Science for Leisure Hours by Richard A. Proctor. Squaring the Circle. There must be a singular charm about insoluble problems, since there are never wanting persons who are willing to attack them. I doubt not that at this moment there are persons who are devoting their energies to squaring the circle, in the full belief that important advantages will accrue to science, and possibly a considerable pecuniary profit to themselves, if they could succeed in solving it. Quite recently, applications have been made to the Paris Academy of Sciences to ascertain what was the amount which that body was authorized to pay over to anyone who should square the circle. So seriously, indeed, was the Secretary annoyed by applications of this sort, that it was found necessary to announce in the daily journals that not only was the Academy not authorized to pay any sum at all, but that it had determined never to give the least attention to those who fancied they had mastered the famous problem. It is a singular circumstance that people have even attacked the problem without knowing exactly what its nature is. One ingenious workman, to whom the difficulty had been propounded, actually set to work to invent an arrangement for measuring the circumference of the circle, and was perfectly satisfied that he had thus solved a problem which had mastered all the mathematicians of ancient and modern times. That we may not fall into a similar error, let us clearly understand what it is that is required for the solution of the problem of squaring the circle. To begin with, we must note that the term squaring the circle is rather a misnomer, because the true problem to be solved is the determination of the length of a circle's circumference when the diameter is known. Of course, the solution of this problem, or as it is termed, the rectification of the circle, involves the solution of the other, or the quadrature of the circle, but it is well to keep the simpler issue before us. Many have supposed that there exists some exact relation between the circumference and the diameter of the circle, and that the problem to be solved is the determination of this relation. Suppose, for example, that the approximate relation discovered by Archimedes, who found that if a circle's diameter is represented by 7, the circumference may be almost exactly represented by 22, were strictly correct, and that Archimedes had proved it to be so, then, according to this view, he would have solved the great problem, and it is to determine a relation of some such sort that many persons have set themselves. Now, undoubtedly, if any relation of this sort could be established, the problem would be solved. But, as a matter of fact, no such relation exists, and the solution of the problem does not require that there should be any relation of the sort. For example, we do not look on the determination of the diagonal of a square whose side is known as an insoluble, or as otherwise than a very simple problem. Yet, in this case, no exact relation exists. We cannot possibly express both the side and the diagonal of a square in whole numbers, no matter what unit of measurement we adopt. Or, to put the matter in another way, we cannot possibly divide both the side and the diagonal into equal parts, which shall be the same along each, no matter how small we take the parts. If we divide the side into 1000 parts, there will be 1,414 such parts, and a piece over in the diagonal. If we divide the side into 10,000 parts, there will be 14,142, and still a little piece over in the diagonal, and so on for ever. Similarly, the mere fact that no exact relation exists between the diameter and the circumference of a circle is no bar whatever to the solution of the great problem. Before leaving this part of the subject, however, I may mention a relation which is very easily remembered, and is very nearly exact, much more so at any rate than that of Archimedes. Write down the numbers 113, 355. That is, the first three odd numbers, each repeated twice over. Then separate the 6 numbers into 2 sets of 3, thus 113/355, and proceed with the division thus indicated. The result, 3.141592 expresses the circumference of a circle whose diameter is 1 correctly to the 6th decimal place, the true relation being 3.14159265. Again, many people imagine that mathematicians are still in a state of uncertainty as to the relation which exists between the circumference and the diameter of the circle. If this were so, scientific societies might well hold out a reward to anyone who could enlighten them. For the determination of this relation, with satisfactory exactitude, may be held to lie at the foundation of the whole of our modern system of mathematics. I need hardly say that no doubt whatever rests on the matter. 100 different methods are known to mathematicians by which the circumference may be calculated from the diameter with any required degree of exactness. Here is a simple one, for example. Take any number of the fractions formed by putting 1 as a numerator over the successive odd numbers. Add together the alternate ones, beginning with the first, which of course is unity. Add together the remainder. Subtract the second sum from the first. The remainder will express the circumference, the diameter being taken as unity, to any required degree of exactness. We have merely to take enough fractions. The process would of course be a very laborious one if great exactness were required, and as a matter of fact, mathematicians have made use of much more convenient methods for determining the required relation, but the method is strictly exact. The largest circle we have much to do with in scientific questions is the Earth's equator. As a matter of curiosity, we may inquire what the circumference of the Earth's orbit is. But as we are far from being sure of the exact length of the radius of that orbit, that is, of the Earth's distance from the Sun, it is clear that we do not need a very exact relation between the circumference and the diameter in dealing with that enormous circle. Confining ourselves, therefore, to the circle of the Earth's equator, let us see what exactness we seem to require. We will suppose for a moment that it is possible to measure round the Earth's equator without losing count of a single yard, and that we want to gather from our estimate what the diameter of this great circle may be. This seems indeed the only use to which, in this case, we can put our knowledge of the relationship we are dealing with. We have then a circle some 25,000 miles round, and each mile contains 1,760 yards. Or in all there are some 44 million yards in the circumference, and therefore, roughly, some 14 million yards in the diameter of this great circle. Hence, if our relation is correct within a 14 millionth part of the diameter, or a 44 millionth part of the circumference, we are safe from any error exceeding a yard. All we want then is that the number expressing the circumference, the diameter being unity, should be true to the 8th decimal place, as quoted above. But, as I have said, mathematicians have not been content with a computation of this sort. They have calculated the number not to the 8th, but to the 620th decimal place. Now, if we remember that each new decimal makes the result 10 times more exact, we shall begin to see what a waste of time there has been in this tremendous calculation. We all remember the story of the horse which had 24 nails in its shoes, and was valued at the sum obtained by adding together a farthing for the first nail, a halfpenny for the next, a penny for the next, and so on, doubling 24 times. The result was counted by thousands of pounds. The old miser, who paid at a similar rate for a grave 18 feet deep, doubling for each foot, killed himself when he heard the total. But now consider the effect of multiplying by 10 620 times. A fraction with that enormous number for denominator and unity for numerator expresses the minuteness of the error which would result if the long value of the circumference were made use of. Let an illustration show the force of this. It has been estimated that light, which could 8 times circle the earth in a second, takes 50,000 years in reaching us from the faintest stars seen in Lord Rosse's giant reflector. Suppose we knew the exact length of the tremendous line which extends from the earth to such a star, and wanted for some inconceivable purpose to know the length of the circumference of a circle of which that line was the radius. The value deduced from the above-mentioned calculation of the relation between the circumference and the diameter would differ from the truth by a length which would be imperceptible under the most powerful microscope ever yet constructed. Nay, the result we have conceived, enormous as it is, might be increased 1,000,000-fold, or 1,000,000 times 1,000,000-fold, with the same result, and the area of the circle formed with this increased radius would be determinable with so much accuracy that the error, if presented in the form of a minute square, would be utterly imperceptible under a microscope 1,000,000 times more powerful than the best ever yet constructed by man. Not only has the length of the circumference been calculated once in this unnecessarily exact manner, but a second calculator has gone over the work independently. The two results are, of course, identical, figure for figure. It will be asked then, what is the problem about which so great a work has been made? The problem is, in fact, utterly insignificant. Its only interest lies in the fact that it is insoluble, a property which it shares along with many other problems, as the trisection of an angle, the duplication of a cube, and so on. The problem is simply this: having given the diameter of a circle to determine by a geometrical construction in which only straight lines and circles shall be made use of, the side of a square equal in area to the circle. As I have said, the problem is solved if by a construction of the kind described we can determine the length of the circumference, because then the rectangle under half this length and the radius is equal in area to the circle, and it is a simple problem to describe a square equal to a given rectangle. To illustrate the kind of construction required, I give an approximate solution, which is remarkably simple, and, so far as I am aware, not generally known. Describe a square about the given circle, touching it at the ends of two diameters, AOB, COB, at right angles to each other, and join CA. Let COAE be one of the quarters of the circumscribing square, and from E draw EG, cutting off from AO a fourth part, AG, of its length, and from AC the portion AH. Then three sides of the circumscribing square together with AH are very nearly equal to the circumference of the circle. The difference is so small that in a circle 2 feet in diameter it would be less than the 200th part of an inch. If this construction were exact, the great problem would have been solved. One point, however, must be noted. The circle is, of all curved lines, the easiest to draw by mechanical means. But there are others which can be so drawn, and if such curves as these be admitted as available, the problem of the quadrature of the circle can be readily solved. There is a curve, for instance, invented by Dinostratus, which can readily be described mechanically, and has been called the quadratrix of Dinostratus, because it has the property of thus solving the problem we are dealing with. As such curves can be described with quite as much accuracy as the circle, for, be it remembered, an absolutely perfect circle has never yet been drawn, we see that it is only the limitations which geometers have themselves invented that give this problem its difficulty. Its solution has, as I have said, no value, and no mathematician would ever think of wasting a moment over the problem. For this reason, simply that it has long since been demonstrated to be insoluble by simple geometrical methods, so that when a man says he has squared the circle, and many will say so if one will only give them a hearing, he shows that either he wholly misunderstands the nature of the problem, or that his ignorance of mathematics has led him to mistake a faulty for a true solution. End of section 30.
Section 31 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Light Science for Leisure Hours by Richard A. Proctor. A New Theory of Achilles' Shield. A distinguished classical authority has remarked that the description of Achilles' shield occupies an anomalous position in Homer's Iliad. On the one hand, it is easy to show that the poem, for the description may be looked on as a complete poem, is out of place in the Iliad. On the other, it is no less easy to show that Homer has carefully led up to the description of the shield by a series of introductory events. I propose to examine briefly the evidence on each of these points, and then to exhibit a theory respecting the shield which may appear bizarre enough on a first view, but which seems to me to be supported by satisfactory evidence. An argument commonly urged against the genuineness of the shield of Achilles is founded on the length and labored character of the description. Even Grote, whose theory is that Homer's original poem was not an Iliad but an Achilleus, has admitted the force of this argument. He finds clear evidence that from Book 2 to Book 20 Homer has been husbanding his resources for the more effective description of the final conflict. He therefore concedes the possibility that the shield of Achilles may be an interpolation, perhaps the work of another hand. It appears to me, however, that the mere length of the description is no argument against the genuineness of the passage. Events have, indeed, been hastening to a crisis up to the end of Book 17, and the action is checked in a marked manner by the Oplopeia in Book 18. Yet it is quite in Homer's manner to introduce between two series of important events an interval of comparative inaction, or at least of events wholly different in character from those of either series. We have a marked instance of this in Books 9 and 10. Here the appeal to Achilles and the night adventure of Diomed and Ulysses are interposed between the first victory of the Trojans and the great struggle in which Patroclus is slain, and Agamemnon, Ulysses, Diomed, Machaon, and Eurypylus wounded. In fact, one cannot doubt that in such an arrangement Homer exhibits admirable taste and judgment. The contrast between action and inaction, or between the confused tumult of a heady conflict and the subtle advance of the two Greek heroes, is conceived in the true poetic spirit. The dignity and importance of the action and the interest of the interposed events are alike enhanced. Indeed, there is scarcely a noted author whose works do not afford instances of corresponding contrasts. How skilfully, for example, has Shakespeare interposed the bald, disjointed chat of the sleepy porter between the conscience-wrought horror of Duncan's murderers, and the horror, 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 which tongue nor heart could not conceive nor name, of his faithful followers. Nor will the reader need to be reminded of the frequent and effective use of the contrast between the humorous and the pathetic by others. The laboured character of the description of the shield is an argument, though not perhaps a very striking one, for the independent origin of the poem. But the arguments on which I am disposed to lay most stress lie nearer the surface. Scarcely anyone, I think, can have read the description of the shield without a feeling of wonder that Homer should describe the shield of a mortal hero as adorned with so many and such important objects. We find the sun and moon, the constellations, the waves of ocean, and a variety of other objects better suited to adorn the temple of a great deity than the shield of a warrior, however noble and heroic. The objects depicted even on the aegis of Zeus are much less important. There is certainly no trace in the Iliad of a wish on Homer's part to raise the dignity of mortal heroes at the expense of Zeus, yet the aegis is thus succinctly described. Fringed round with ever-fighting snakes, though it was drawn to life, the miseries and deaths of fight, in it frowned bloody strife. In it shone sacred fortitude, in it fell pursuit flew, in it the monster Gorgon's head, in which held out to view, were all the dire ostents of Jove. Chapman's translation. 5 lines here, as in the original, suffice for the description of Jove's aegis, while 130 lines are employed in the description of the celestial and terrestrial objects depicted on the shield of Achilles. Another circumstance attracts notice in the description of Achilles' armor: the disproportionate importance attached to the shield. Undoubtedly, the shield was that portion of a hero's armor which admitted of the freest application of artistic skill. Yet this consideration is not sufficient to account for the fact that while so many lines are given to the shield, the helmet, corselet, and greaves are disposed of in 4. But the argument on which I am inclined to lay most stress is the occurrence elsewhere of a description which is undoubtedly only another version of the shield of Achilles. The shield of Hercules occurs in a poem ascribed to Hesiod, but whatever opinion may be formed respecting the authorship of the description, there can be no doubt that it is not Hesiod's work. It exhibits no trace of his dry, didactic, somewhat heavy style. Elton ascribes the shield of Hercules to an imitator of Homer, and in support of this view points out those respects in which the poem resembles and those in which it is inferior to the shield of Achilles. The two descriptions are, however, absolutely identical in many places, and this would certainly not have happened if one had been an honest imitation of the other. And those parts of the shield of Hercules which have no counterparts in the shield of Achilles are too well conceived and expressed to be ascribed to a very inferior poet, a poet so inferior as to be reduced to the necessity of simply reproducing Homer's words in other parts of the poem. Those parts which admit of comparison, where, for instance, the same objects are described, but in different terms, are certainly inferior in the shield of Hercules. The description is injured by the addition of unnecessary or inharmonious details. Elton speaks accordingly of these portions as if they were expansions of the corresponding parts of the shield of Achilles. This appears to me a mistake. It seems far more likely that both descriptions are by the same poet. It is not necessary for the support of my theory that this poet should be Homer, but I think both descriptions show undoubted traces of his handiwork. Indeed, all known imitations of Homer are so easily recognizable as the work of inferior poets that I should have thought no doubt could exist on this point, but for the attention which the German theory respecting the Iliad has received. Assigning both poems to Homer, the Shield of Hercules may be regarded not as an expansion in parts of the Shield of Achilles, but as an earlier work of Homer's, improved and pruned by his maturer judgment when he desired to fit it into the plan of the Iliad. Or rather, each poem may be looked on as an abridgment, the Shield of Hercules the earlier, of an independent work on a subject presently to be mentioned. It is next to be shown that in the events preceding the Oplopeia there is a preparation for the introduction of a separate poem. In the first place, every reader of Homer is familiar with the fact that the poet constantly makes use, when occasion serves, of expressions, sentences, often even of complete passages, which have been already applied in a corresponding, or occasionally even in a wholly different relation. The same epithets are repeatedly applied to the same deity or hero. A long message is delivered in the very words which have been already used by the sender of the message. In one well-known instance, in Book II, not only is a message delivered thus, but the person who has received it repeats it to others in precisely the same terms. In the combat between Hector and Ajax, Book VI, the flight of Ajax's spear and the movement by which Hector avoids the missile are described in 6 lines, differing only as to proper names from those which had been already used in describing the encounter between Paris and Menelaus, Book III. This peculiarity would be a decided blemish in a written poem. Tennyson, indeed, occasionally copies Homer's manner. For instance, in Enid, he twice repeats the line, "As careful robins eye the delver's toil," but with a good taste which prevents the repetition from becoming offensive. The fact is that the peculiarity marks Homer as the singer, not the writer, of poetry. I would not be understood as accepting the theory according to which the Iliad is a mere string of ballads. I imagine that no one who justly appreciates that noble poem would be willing to countenance such a theory, but that the whole poem was sung by Homer at those prolonged festivals which formed a characteristic peculiarity of Achaean manners seems shown not only by what we learn respecting the later rhapsodists, but by the internal evidence of the poem itself. Homer, reciting a long and elaborate poem of his own composition, occasionally varying the order of events, or adding new episodes, extemporized as the song proceeded, would exhibit the peculiarity invariably observed in the improvisatore, of using more than once expressions, sentences, or passages which happened to be conveniently applicable. The art of extemporizing depends on the capacity for composing fresh matter while the tongue is engaged in the recital of matter already composed. Anyone who has watched a clever improvisatore cannot fail to have noticed that though gesture is aptly wedded to words, the thoughts are elsewhere. In the case, therefore, of an improvisatore, or even of a rhapsodist reciting from memory, the occasional recurrence of a well-worn form of words serves as a relief to the strained invention or memory. We have reason, then, for supposing that if Homer had, in his earlier days, composed a poem which was applicable, with slight alterations, to the story of the Iliad, he would endeavour, by a suitable arrangement of the plan of his narrative, to introduce the lines whose recital had long since become familiar to him. Evidence of design in the introduction of the Shield of Achilles certainly does not seem wanting. It is by no means necessary to the plot of the Iliad that Achilles should lose the celestial armour given to Peleus as a dowry with Thetis. On the contrary, Homer has gone out of his way to render the labours of Vulcan necessary. Patroclus has to be so ingeniously disposed of that, while the armour he had worn is seized by Hector, his body is rescued, as are also the horses and chariot of Achilles. We have the additional improbability that the armor of the great Achilles should fit the inferior warriors Patroclus and Hector. Indeed, that the armor should fit Hector, or rather that Hector should fit the armor, the aid of Zeus and Ares has to be called in. To this Jove's sable brows did bow, and he made fit his limbs to those great arms, to fill which up the war god entered him, austere and terrible, his joints and every part extends, with strength and fortitude. Chapman's translation. It is clear that the narrative would not have been impaired in any way, while its probability and consistency would have been increased if Patroclus had fought in his own armor. The death of Patroclus would in any case have been a cause sufficient to arouse the wrath of Achilles against Hector, though certainly the hero's grief for his armor is nearly as poignant as his sorrow for his friend. It appears probable, then, that the description of Achilles' shield is an interpolation, the poet's own work, however, and brought in by him in the only way he found available. The description clearly refers to the same object which is described, here also only in part, in the shield of Hercules. The original description doubtless included all that is found in both shields, and probably much more. What, then, was the object to which the original description applied? An object, I should think, far more important than a warrior's shield. I imagine that anyone who should read the description without being aware of its accepted interpretation would consider that the poet was dealing with an important series of religious sculptures, possibly that he was describing the dome of a temple adorned with celestial and terrestrial symbols. In Egypt there are temples of a vast antiquity having a dome on which a zodiac, or more correctly, a celestial hemisphere, is sculptured with constellation figures. And we now learn from ancient Babylonian and Assyrian sculptures that these Egyptian zodiacs are in all probability merely copies, more or less perfect, of yet more ancient Chaldean zodiacs. One of these Babylonian sculptures is figured in Rawlinson's Ancient Monarchies. It seems probable that in a country where Sabianism or star worship was the prevailing form of religion, yet more imposing proportions would be given to such zodiacs than in Egypt. My theory, then, respecting the shield of Achilles is this. I conceive that Homer, in his Eastern travels, visited imposing temples devoted to astronomical observation and star worship, and that nearly every line in both shields is borrowed from a poem in which he described a temple of this sort, its domed zodiac, and those illustrations of the labors of different seasons and of military or judicial procedures, which the astrological proclivities of star worshippers led them to associate with the different constellations. I think there are arguments of some force to be urged in support of this theory, fanciful as it may seem at a first view. In the first place, it is necessary that the constellations recognized in Homer's time, not necessarily or probably by Homer, should be distinguished from later inventions. Aratus, writing long after Homer's date, mentions 45 constellations. These were probably derived, without exception, from the globe of Eudoxus. Remembering the tendency which astronomers have shown in all ages to add to the list of constellations, we may assume that in Homer's time the number was smaller. Probably there were some 15 northern and 10 southern constellations besides the 12 zodiacal signs. The smaller constellations mentioned by Aratus doubtless formed parts of larger figures. Anyone who studies the heavens will recognize the fact that the larger constellations have been robbed of their just proportions to form the smaller asterisms. Corona Borealis was the right arm of Bootes, Ursa Minor was a wing of Draco, now wingless and no longer a dragon, and so on. Secondly, it is necessary that the actual appearance of the heavens, with reference to the position of the pole in Homer's time, should be indicated. For my present purpose, it is not necessary that we should know the exact date at which the most ancient of the zodiac temples were constructed, or to which they were made to correspond. There are good reasons, though this is not the proper place for dwelling upon them, for supposing that the great epoch of reference amongst ancient astronomers preceded the Christian era by about 2200 years. Be this as it may, any epoch between the date named and the probable date at which Homer flourished, say 9 or 10 centuries before the Christian era, will serve equally well for my present purpose. Now, if the effects of equinoctial precession be traced back to such a date, we are led to notice two singular and not uninteresting circumstances. First, the pole of the heavens fell in the central part of the great constellation Draco, and secondly, the equator fell along the length of the great sea serpent Hydra, in one part of its course, and elsewhere to the north of all the ancient aquatic constellations, save that one half of the northernmost fish of the zodiac pair lay north of the equator. Thus, if a celestial sphere were constructed with the equator in a horizontal position, the dragon would be at the summit, Hydra would be extended horizontally along the equator, but with his head and neck reared above that circle, and Argo, Cetus, Capricornus, Piscis Australis, and Pisces, save one half of the northernmost, would lie below the equator. It may also be mentioned that all the bird constellations were then, as now, clustered together not far from the equator, Cygnus, the farthest from the equator, being 10 degrees or so nearer to that circle than at present. Now, let us turn to the two shields, and see whether there is anything to connect them with zodiac temples, or to remind us of the relations exhibited above. To commence with the shield of Achilles, the opening lines inform us that the shield showed the starry lights that heaven's high convex crowned, the Pleiads, Hyads with the northern team, and great Orion's more refulgent beam. And here in Achilles' shield the list of constellations closes, but it is remarkable that in the shield of Hercules, while the above lines are wanting, we find lines which clearly point to other constellations. Remembering what has just been stated about Draco, it seems at the least a singular coincidence that we should find the center or boss of the shield occupied by a dragon. The scaly horror of a dragon coiled, full in the central field unspeakable, with eyes oblique retorted that aslant shot gleaming flame. Elton's translation. We seem also to find a reference to the above-named relations of the aquatic constellations, and specially to the constellation Pisces. In the midst, full many dolphins chased the fry, and showed as though they swam the waters to and fro, darting tumultuous, too, of silver scale, panting above the wave. For we learn from both shields that the waves of ocean were figured in a position corresponding with the above-mentioned position of the celestial equator, beneath which, that is, in the ocean, on our assumption, the aquatic constellations were figured. The description of the ocean in the shield of Hercules contains also some lines in which we seem to see a reference to the bird constellations close above the equator. Rounding the utmost verge the ocean flowed, as in full swell of waters, and the shield, all variegated, with whole circle bound. Swans of high hovering wing there clamoured shrill, who also skimmed the breasted surge with plume innumerous. Near them fishes midst the waves frolicked in wanton bounds. In the shield of Achilles no mention is made of Perseus, but in the shield of Hercules this well-known constellation seems described in the lines There was the knight of fair-haired Danae born, Perseus, nor yet the buckler with his feet touched, nor yet distant hovered, strange to see, for nowhere on the surface of the shield he rested, so the crippled artist god, illustrious, framed him with his hands in gold. Bound to his feet were sandals winged, a sword of brass with hilt of sable ebony, hung round him from the shoulders by a thong. The visage grim of monstrous Gorgon all his back o'erspread, the dreadful helm of Pluto clasped the temples of the prince. I think that one may recognize a reference to the twins Castor and Pollux, the wrestler and boxer of mythology, in the words, "But in another part were men who wrestled, or in gymnic fight wielded the cestus." Orion is not mentioned by name in the Shield of Hercules as in the other, but Orion, Lepus, and the two dogs seem referred to. Elsewhere men of chase were taking the fleet hares, two keen-toothed dogs hounded beside these ardent in pursuit, those with like ardour doubling in their flight. In each shield we find a reference to the operations of the year, hunting and pasturing, sowing, ploughing, and harvesting. It is hardly necessary to point out the connection between these operations and astronomical relations. That this connection was fully recognized in ancient times is shown in the works and days of Hesiod. We find also in Egyptian zodiacs clear evidence that these operations, as well as astronomical symbols or constellations, were pictured in sculptured domes. The judicial, military, and other proceedings described in the Shield of Achilles were also supposed by the ancients to have been influenced by the courses of the stars. If there were no evidence that ancient celestial spheres presented the constellations above referred to, I might be disposed to attach less weight to the coincidences here presented, but the phenomena of Aratus affords sufficient testimony on this point. In the first place, that work is of great antiquity, since Aratus flourished 2 centuries and a half before the Christian era, but it is well known that Aratus did not describe the results of his own observations. The positions of the constellations, as recorded by him, accord neither with the date at which he wrote, nor with the latitude in which he lived. It is generally assumed, chiefly on the authority of Hipparchus, that Aratus borrowed his knowledge of astronomy from the sphere of Eudoxus. But we must go much farther back even than the date of Eudoxus before we can find any correspondence between the appearance of the heavens and the description given by Aratus. Thus we may very fairly assume that the origin of the constellations, as distinguished from their association with certain circles of the celestial sphere, may be placed at a date preceding, perhaps by many generations, that at which Homer flourished. Indeed, there have not been wanting those who find in the ancient constellations the record of the early history of man. According to their views, Orion is Nimrod, the giant, as the Arabic name of the constellation implies, the mighty hunter, as the dogs and hare beside him signify. The centaur bearing a victim towards the altar is Noah. Argo, the stern of a ship, is the ark, as of old it might be seen on Mount Ararat. Corvus is the crow sent forth by Noah, and the bird is placed on Hydra's back to show that there was no land on which it could set its foot. The figure, now called Hercules, but of old Engonasin, or the kneeler, and described by Aratus as a man doomed to labor, is Adam. His left foot treads on the dragon's head, in token of the saying, "It shall bruise thy head," and Serpentarius, or the serpent-bearer, is the promised seed. Of course, if we accept these views, we have no difficulty in understanding that a poet so ancient as Homer should refer to the constellations which still appear upon celestial spheres; and, in any case, the mere question of antiquity presents, as we have already shown, little difficulty. But there is one difficulty, a notice of which must close this paper, already carried far beyond the limits I had proposed to myself. It may be thought remarkable that heroes of Greek mythology, as Perseus and Orion, should be placed by Homer, or even by Aratus, in spheres which are undoubtedly of Eastern origin. Now, it may be remarked first of Homer that many acute critics consider the whole story of the Iliad to be, in reality, merely an adaptation of an Eastern narrative to Greek scenes and names. It is pointed out that whereas the catalogue in Book II reckons upwards of 100,000 men, only 10,000 fought at Marathon, and whereas there are counted no less than 1,200 ships in the catalogue, there were but 271 at Artemisium, and at Salamis but 378. However this may be, we have the distinct evidence of Herodotus that the Greek mythology was derived originally from foreign sources. He says, "All the names of the gods in Greece were brought from Egypt," an opinion in which Diodorus and other eminent authorities concur. But it is the opinion of acute modern critics that we must go beyond Egyptian to Assyrian or Indian, perhaps even to Hebrew sources, for the origin of Greek mythology. Layard has ascribed to Niebuhr the following significant remarks: "There is a want in Grecian art which neither I nor any man now alive can supply. There is not enough in Egypt to account for the peculiar art and the peculiar mythology which we find in Greece. That the Egyptians did not originate it I am convinced, though neither I nor any man now alive can say who were the originators. But the time will come when, on the borders of the Tigris and Euphrates, those who come after me will live to see the origin of Grecian art and Grecian mythology." From The Student, June, 1868. End of Section 31. Recording by Linda Johnson. End of Light Science for Leisure Hours by Richard A. Proctor.